Good morning. So today we are going to start with the next topic, that is preparations and properties of amines and the diazonium salts. Let us see what is the outline for the lecture today. We will start with the introduction of amines. We will see what amines are and how they are classified. Next we will see their structure and we will see what are the special features associated with the structure of the amines. Next would be their physical properties, where in detail we are going to study the solubility of amines as well as their variation in boiling point. Next we would discuss the methods of preparation of the amino compounds, and in the end there will be questions based on what we have learned today. So let us start by defining what are amines. Now all of you are aware of ammonia. Ammonia is nitrogen bonded to 3 hydrogen atoms. When one of these hydrogen atoms is replaced by R, the compounds that we get are called amines. So I can represent amine like this. Replace at least one hydrogen by R and I get amine. Now this R can be aliphatic. In that case, the amine will be called the aliphatic amine. For example, I can write methylamine. In case this R group is aromatic, then the amine will be called an aromatic amine. One example can be aniline. There is another class of amines which are when this R group is an aryl alkyl group. For example, you can have benzyl group. In that case, the amines will be called aryl alkyl amines. The example can be benzylamine. So you can see these are the 3 types of amines that you can have. Now you can see that the structure that I have drawn here, these are some of the examples of amines that you find in nature. This compound is trimethylamine. This compound is nicotine, which you get in cigarettes. And another compound is cocaine, which is an opium alkaloid found from opium. Now these amine compounds, they are found in both plants as well as animals. 2 examples that I can give you of naturally occurring amines. One is caffeine, which you get in tea. Whenever you feel that your mind is sluggish and you are feeling sleepy, one wants to have tea. The chief constituent of tea is caffeine, which is an amino compound. Okay. Another example that I can give you for amino compounds is a compound that is called quinine, which is obtained from the bark of cinchona tree. And this quinine, is used in the treatment of malaria. There are other derivatives of quinine now available. However, initially the treatment of malaria was done from this compound quinine, which is obtained from the bark of cinchona tree. So 2 examples I have given you to show that means they are found in nature and they are very useful to us. Now I said that amines are obtained by replacement of hydrogen in ammonia by alkyl, aryl or an aryl alkyl group. Depending upon number of hydrogens which are replaced in ammonia, the amines can be classified into 4 different types. Okay, let us see. Now, when one of the hydrogens on ammonia is replaced by alkyl group, you will get a compound which will look like this. Nitrogen is bonded to one alkyl group and 2 hydrogens. This will be an example of a primary amine. So, you have one alkyl group and 2 hydrogens which are bonded to nitrogen. The second case would be when 2 of the hydrogens in nitrogen are replaced by alkyl group. So, the structure will look like this. You can see there are 2 alkyl groups or aryl groups attached to nitrogen and there is 1 hydrogen. So, these compounds are called secondary amines. Third case would be when all the 3 hydrogens have been replaced by the alkyl or the aryl group. In that case, the structure of the compound will be something like this. Okay, so there are no hydrogens attached to this compound. This will be called a tertiary amine. And there is one more category of amine. Those are called the quaternary ammonium salt, where you have 4 alkyl groups or aryl groups being attached to nitrogen and nitrogen carrying a positive charge. You know, these compounds we can say are derivatives of the ammonium salts. They are called quaternary ammonium salts. So, depending upon number of R groups which are surrounding nitrogen, the amine compounds are classified into 4 types. Those are the primary amines. I have told you there is 1 alkyl group and there are 2 hydrogens. Secondary amines, there are 2 alkyl groups and 1 hydrogen. Tertiary amines, there are 3 alkyl groups and 1 hydrogen. And quaternary salts, where there are 4 alkyl groups attached to nitrogen. Okay. I have some examples here. You can see here, this compound, there is only 1 alkyl group and that alkyl group is a tertiary butyl group, right? Besides that, there are 2 hydrogens attached to this nitrogen. So, this will be an example of a primary amine and it will be called a tertiary butyl amine, right? The next example is this compound. Common name of this compound is piperidine. You can see here there is 1 hydrogen attached to nitrogen and there are 2 alkyl substituents, right? So, this is an example of a secondary amine, right? Third is an example where you can see nitrogen does not have a hydrogen attached to it and it has 3 different alkyl or aryl groups attached to it. So, it will be an example of a tertiary amine, right? And fourth is an example of a quaternary salt. You can see their nitrogen here is surrounded by 4 R groups, you know. This is a quaternary ammonium salt. Okay. Another class of amines, they are categorized under aromatic amines. These compounds are again very, very important in medicines, in dyes and all these compounds. They are called the heterocyclic amines. These are some of the examples that I have given you here. Now, so far, all the aromatic compounds that you have come across, they have only carbon in the ring, right? For example, if you take benzene, right? I have written one aniline, phenol. All these compounds, they have carbon only in the ring, so they are called carbocyclic compounds. They have only carbon in the ring. Now these are heterocyclic compounds where what happens is one or more carbon in the ring is replaced by hetero. Hetero means different atom other than carbon. In this case, because we are studying amines, we will restrict ourselves only to nitrogen substituents. Okay? So these are heterocyclic amines. Okay, 2-3 examples you can see. This is pyridine, this is pyrrole, because you get questions on basicity based on this in IITs. So it is important that you know some of these structures. Pyridine, especially pyrrole, this one pyrrolidine, and this compound is piperidine. So at least these 4 structures you should know. Okay, pyridine, pyrrole, pyrrolidine, and piperidine. Okay. Now, as we have been doing in the earlier classes, since you know the IUPAC nomenclature, we will try to learn the common names of some of the amines, know how to name them. Okay, a common name of amines is given like they are named as alkyl or aryl amines, like so. Let us look at these few examples that I have for you. This compound is methylamine, right? You can see here what is this group. This is again a tertiary butyl group. So this is tertiary butylamine. We have seen it in the last slide. This ring is cyclopentyl, right? And there are 2 cyclopentyl groups, so it will be dicyclopentylamine, right? And this one is tertiary butylamine. You can see there is one cyclopentyl group, so it becomes dicyclopentyl because there are 2 cyclopentyl groups. So this becomes dicyclopentylamine. So it is ethyl group. Okay, so this compound is triethylamine. Because there are 3 ethyl groups, so it becomes triethylamine, right? I have few more examples. Now you see you have nitrogen here being bound to 2 phenyl rings. So it becomes diphenylamine. Okay. The next compound is there is a cyclopentyl group and there is a methyl group. When there are 2 different alkyl groups attached, then while naming them, you have to follow the alphabetical order. This will be cyclopentyl methylamine, right? And this is the last example. There is a ethyl group and there is a methyl group. There are 2 ethyl groups, so this becomes diethyl methylamine, right? Okay. Now let us see the uses of amines in our daily life. The first use of amines is as dyes. They are used as dyes, especially methyl orange is an example of an azo dye. If I write the structure of methyl orange for you. It's a big molecule. Now, this compound is used as an acid-base indicator in the titrations. Okay? It has two distinct colors. In the acidic pH, it is red in color. As you go on increasing the pH from 3 to about 4.4, you find that the colors changes. From red, it becomes orange, and finally, it becomes yellow. Oh, at about 4.4, this is yellow in color. So used as an acid-base indicator in the titrations. Okay. The next is the use as neurotransmitters. These are chemicals which are used in transmitting signals from the brain across the nerve cells. Okay. So three examples I have taken. They're all amines. One is adrenaline. Second one is dopa. And third one is serotonin. So, Alzheimer's, you have heard about Alzheimer's? Alzheimer's is loss of memory. The loss of memory is because of this compound, the imbalance of serotonin in the body, which is responsible for Alzheimer and also loss of sleep. Okay. The next use is that of proteins. Proteins are in school since 7th, 8th, you have learned them. They are what? They are bodybuilding food. Protein is a bodybuilding food which you learned in school as kids. Now, what are proteins? Proteins are made from amino acids. One example I will give you. This compound is called lysine. Okay, this is one amino acid. Now, amino acids, they combine together to form proteins, which are responsible for growth and wear and tear. They take care of wear and tear in the body. Another example of amines is as drugs. Have you heard the names of morphine, nicotine, cocaine? They are all habit forming drugs. In case of cancer patients, when the normal painkillers don't work, they are given injections of morphine. Okay? It is not administered to normal patients because this is habit forming. They're all habit forming drugs. Okay? Another application of the amine compounds is as decongestants. When you have cold and cough, the doctor prescribes you syrups. One example is Benadryl. Okay, so that is a decongestant, again an amino compound. And another use is as antidepressants. When some person is suffering from depression, okay, the doctor will prescribe some chemicals, some medicines, and those are working as antidepressants. They are nothing but they are amino compounds. Okay, so you have seen how vastly and closely related are these amino compounds to our daily life. Okay. Next, let us come to their structure of amine. Now, you have studied the structure of ammonia. What is the hybridization on nitrogen? The hybridization on nitrogen is sp3. So that is the structure of ammonia, where you have nitrogen, which is sp3 hybridized, and it has a pyramidal geometry, right? A distorted tetrahedra. Now, when we replace this hydrogen by R, the primary, secondary or the tertiary amines, they have exactly the same structure. They will also be pyramidal, nitrogen having sp3 hybridization. Now, if nitrogen is sp3 hybridized, what do you expect the geometry of the molecule to be? It should be tetrahedral for sp3 hybridized molecule. It should be tetrahedral, and then the bond angle should be 109 degree 28 minutes. Yeah? The expected bond angle is correct. However, in case of ammonia also, I believe you know that the bond angle is 107 degree. Okay. Same will be the case with primary as well as secondary amines, where you will find that the bond angle will be 107 degrees. In case of tertiary amines, you find that the bond angle slightly increases to about 108 degrees. Now, there are two questions that we will have to answer here. The first question is why the bond angle shrinks from an expected value of 109 degree 28 minutes for primary and secondary amines. And the second question that we will have to answer is why in case of tertiary amines the bond angle slightly increases, right? Yes. This is your primary amine. This is secondary amine. And this is the tertiary amine. Now what happens here is because of the lone pair, present here, there is a repulsion between the lone pair and the bond pair. The bond pair on the CN bond here, because of which the bond angle is shrinking from a conventional value of 109 degree 28 minute, it goes down to 107 degrees, right? About 107 degrees here and here for primary and secondary amines. But what happens in case of tertiary amines is that now, yes, you have three bulky groups here. Now these bulky groups, there is a steric crowding because of the presence of three bulky groups, and because of which what happens is the bond pairs, they start repelling each other. So the bond pair repulsion becomes more than the lone pair bond pair repulsions. Because of which the bond angle will slightly expand and it goes to about 108 degrees, right? Okay, let us see in the next slide. You can see I have shown here, this is the three-dimensional representation of the molecule here that I have shown. This is the blue color is nitrogen, and these gray color are the three methyl groups. These are the three hydrogens, right? There you can see. In case of ammonia, the bond angle is 107 degree. In case of tertiary amine, it has expanded to 108 degrees, right? Now, let us now discuss a very important characteristic of amines, and that is their chirality and their optical activity. Now, in case of carbon compounds, you have learned that in case there are 4 different groups attached to carbon, that carbon is chiral, and it will show optical activity. It will show optical activity means it will exist as a pair of enantiomers, right, which are resolvable. So you can isolate both the enantiomers. Now, if we apply the same concept to the nitrogen compounds, okay, let us write one compound. This is a secondary amine, okay. If you see on the same lines, we can say that this particular amine also has 4 different groups attached to it if we consider the lone pair as the 4th group, right? There is methyl, ethyl, hydrogen and lone pair being the 4th group. So on the same argument, you expect that these nitrogen compounds should also be chiral. They should exist as a pair of enantiomers which are resolvable. Okay. However, in practice, what happens is, in spite of their chirality, their enantiomers cannot be isolated. The reason is that the energy difference between the enantiomers is very, very small. It is of the order of around 25 kilojoules per mole. So what is the reason why the enantiomers are not isolable? It is because of the small enantiomer, the energy difference between the two enantiomers. There can easily change from the one enantiomeric form to the other enantiomeric form. That means R can go to S or S can go to R, right? Let us write how this happens. Now let us say this is one of the enantiomers. What is the hybridization on nitrogen here? The hybridization on nitrogen is sp3. sp3. Now what happens is that slowly this molecule changes from an sp3 hybridization to an sp2 hybridization. This is the pyramidal geometry here. So it changes from an sp3 hybridization to a planar sp2 hybridization, and through this planar intermediate structure, it changes back to the other enantiomeric form. Okay, and this phenomena is called pyramidal inversion. It is called nitrogen inversion, or it is called the pyramidal inversion. You can see here, I have shown one enantiomer here, and it has changed to the other enantiomer. How that change is taking place, I have shown here. I will show you in the next slide also. You can see here. This is the pyramidal geometry, the S enantiomer that I have written here. It goes to the planar state where you can see the hydrogen, methyl and the ethyl group. They are in the same plane. Okay? From this planar geometry, it goes back again to the pyramidal state and there is inversion of configuration taking place. Okay? So please remember, what is the important requirement for this pyramidal inversion to take place? The important requirement is the presence of lone pair of electrons on nitrogen. Only those amine compounds which have 3 different groups attached to it, number one. And second thing is they have lone pair of electrons. That means they should either be a primary amine. Primary amine, will it be chiral? It will not be chiral because there will be 2 hydrogens attached to it, right? So it cannot be a primary amine. So it has to be either a secondary amine with 2 different alkyl groups or a tertiary amine which can exhibit this pyramidal inversion. Okay, so their enantiomeric forms will not be resolvable. Now I just have a small video for you where I will show you how this inversion is taking place so that it gives you a better visualization of the phenomena. Please watch very carefully. This is the sp3 hybridized state here. Okay. Now it will rotate the molecule, but it will still be sp3 hybridized. In the first case, you see, it is rotating. This is the lone pair of electron. Please keep an eye on this. Okay? And these are the 3 different groups. That is nitrogen. Central nitrogen, lone pair of electrons, 3 different groups attached to nitrogen. Now see, abhi tak this is pyramidal geometry so far. Now you see how it will change from a pyramidal geometry to a planar geometry. The lone pair of electrons were earlier occupying the sp3 hybridized orbital. Now in the next stage they will occupy a pure p orbital. See how it happens. Just keep an eye on these bonds. See, can you see they are straightening? Now they are coming in the same plane, right? They come in the same plane. Now the molecule has become planar. Ye tino they are all in the same plane now. And look at this. The lone pair of electrons are now being occupied by a pure p orbital. Okay, so you can see this planarity here and this p pi orbital which is occupying the lone pair of electron. Again it is planar. They have just rotated the molecule, still rotating the molecule so that to give you a better view. Again still planar, you can see they are all in the same plane. Pure p orbital here, planar. Now watch the bonds, how they are twisting. See, they will be bending to my right. Can you see they are bending? They are bending to the right. Again they are changing to the pyramidal geometry. Now again the lone pair of electrons are occupying the sp3 hybridized orbital. Okay? Have you seen? Now you understand how it is taking place from a pyramidal geometry. First the bonds will straighten. They will go to a planar geometry. The lone pair of electrons will occupy a pure p orbital. Again from the planar geometry it goes back to the pyramidal geometry with inversion of configuration taking place. Is that okay? Okay, let's move to the next slide. Now I told you that for pyramidal inversion to take place, you should either have a secondary amine with 2 different R groups or a tertiary amine. That means when they have lone pair of electrons. What about quaternary ammonium salt and there are 4 different groups attached to it? Quaternary ammonium salts cannot exhibit the phenomena of pyramidal inversion because they no longer have lone pair of electrons. Lone pair of electrons is a very important condition for pyramidal inversion to take place. So you will see that if there are 4 different groups attached to nitrogen in a quaternary ammonium salt, it will exhibit optical activity and the two enantiomers can be easily isolated because there will be no pyramidal inversion taking place in that case. Follow me? Okay. Next, let us go to the physical properties of amines. The first physical property that we are discussing is the boiling point. Now, we have learned in the earlier classes that the boiling point of organic compounds largely depends upon their polarity and on their ability to form hydrogen bonds, the strong intermolecular forces of attraction which will determine the boiling points, right? Now, let us write an amine and compare it with alcohol which you have studied earlier, or also carboxylic acids which you have done in the last class. You find that the central atom here is nitrogen, whereas in case of alcohol and in carboxylic acid you have the hydroxyl group, the OH group, right? Now, because of the electronegativity difference between nitrogen and oxygen, oxygen has electronegativity about 3.5, whereas nitrogen has electronegativity of about 3. So what happens is, because of the higher electronegativity difference between oxygen and hydrogen, the polarity of bonds in case of alcohols as well as carboxylic acids is much more than the polarity of bonds in case of amines because of the lower electronegativity difference between the nitrogen and hydrogen. Okay? As a result, what will happen is that the amines will be less polar as compared to alcohols or carboxylic acids. Now, because amines are less polar than alcohols or carboxylic acids, they will form weaker hydrogen bonds. Because the hydrogen bonding will be weaker than in case of alcohols and carboxylic acids, you find that the boiling points of amines will be lower than those of alcohols and carboxylic acids, right? One example I will give you here. That of ethylamine and ethyl alcohol, you find ethylamine has a boiling point of about 20 degrees centigrade, whereas ethyl alcohol has a boiling point of about 78 degrees centigrade. You can see there is huge difference in the boiling point of the corresponding amine and alcohol, right? That is because of the decreased polarity in case of the amino compounds. Now, if you compare the individual molecules here, that is, if I have to compare the boiling point of primary, secondary and the tertiary amines, you find see, secondary amine has 2 hydrogens attached to nitrogen. Sorry, primary amine has 2 hydrogens attached to nitrogen. The secondary amine has only 1 hydrogen, whereas tertiary amine has none. So what you take from here is that the ability to form hydrogen bonds will be maximum in case of primary amines, then followed by secondary amines which have 1 donatable hydrogen, and there will be no hydrogen bonding in case of tertiary amines. Okay, so as the extent of hydrogen bonding decreases when you move from a primary amine to a tertiary amine, their boiling points will also go on decreasing. So the boiling points of the amines will follow the order primary, greater than secondary, greater than tertiary, right? So in the next slide, we will see how the hydrogen bonding can be depicted. Here I have shown the hydrogen bonding for secondary amine. Now it is very easy to write this structure. How to write this structure very quickly? You first write nitrogens like this, put two R groups on each of the nitrogens. Okay, and then add one hydrogen. Join it to nitrogen through hydrogen bond. Then this nitrogen will have one hydrogen which will be bonded to the adjoining nitrogen by hydrogen bond, and so on. So in no time you can write the hydrogen bonding structure of amines, right? That is how you can depict the hydrogen bonding in amines. The next is their solubility. Now we have learned in the earlier classes also that solubility of a compound will depend upon its ability to form hydrogen bonds with water molecules. And we have learned that there are some compounds which act as hydrogen donors. There are some other compounds which act as hydrogen acceptors, like carbonyl compounds which act as hydrogen acceptors. And there are some compounds which can do both, which can act like carboxylic acid, which can act as both hydrogen donors as well as hydrogen acceptors. When you come to the case of amines, you will find that the primary and secondary amines, they can act both as hydrogen donors as well as hydrogen acceptors. So the solubility of primary and secondary amines will be higher in water as compared to that of tertiary amines, which can only, because there is no hydrogen attached to nitrogen, so they will only act as hydrogen acceptors. So the solubility in the order will be primary greater than secondary greater than primary, tertiary, right? Also, if you look at the structure of amine, see, it is this bond which is polar. As the hydrocarbon part increases, the hydrocarbon part is hydrophobic. As the chain length of the hydrophobic part increases, the solubility in water will go on decreasing. So you find that the amines are soluble in water up to C6. Beyond that, they are not soluble in water because the hydrophobic hydrocarbon part now starts to dominate over the polar amino group. Okay? If you look at the aromatic amines, they will be practically insoluble in water because of the presence of the big hydrophobic benzene ring, right? You can see here. So they are expected not to be soluble in water, right? So this is what I was telling you. You can see that the primary or secondary amines, because you have hydrogens attached to nitrogen, they can act as both hydrogen acceptors as well as hydrogen donors. So they form stronger hydrogen bonds. Whereas tertiary amines, because there is no hydrogen attached to nitrogen, they can only act as hydrogen acceptors and their solubility in water is going to be less as compared to those of primary and the secondary amines. Okay. Okay. Next, let us come to a very important aspect of amines, and that is their basicity. Okay. What do you understand by the term base? Any substance which can donate lone pair of electron will exhibit basic character. It will be a Lewis base. Okay. The other way of saying is that basic compounds are those which can accept a proton, right? So any substance which is donating electron pair or it is accepting proton will be basic. Will be a basic or it will be a base, right? Now, how to determine the basicity of a molecule? How to find out whether it is a strong base or it is a weak base? To do so, you can either study or you can compare their Kb or the pKb values, or we can compare the dissociation constants of the conjugate acid, that is the Ka or the pKa. Let us understand what I mean by this. If I have an amine and I dissolve it in acid, because it is a base, it can abstract a proton. So what will be the dissociation constant Kb here? Kb will be correct. This will be Kb. Now, for any substance to be a strong base, the first condition is it should have high Kb, right? The dissociation constant should be high. Or another way of saying it is it should have low pKb, right? Okay. This is when you compare or you define a base in terms of the Kb or the pKb values, the dissociation constants of the base. I said the another way of doing it is in terms of dissociation constant of the conjugate acid, right? What will be the conjugate acid? The corresponding ammonium salt, right? When you dissolve this in water, because this is an acid, it will give away its proton. Right? This will be the dissociation. And so how do you define Ka? Ka will be water being the solvent will be present in large excess, so it is ignored. Okay? That will be the Ka values. So another way of expressing basicity is to say that the Ka value will be low. Low Ka means high pKa, right? So from this discussion, we get two rules to determine or to estimate the basicity of a molecule. It should have high pKb, sorry, it should have high Kb or low pKb, or it should have low Ka or high pK. Okay, now let us see Just now I have told you how it is reacting with water to form the salt. Dissociation expressed in terms of Kb here, and the dissociation being expressed in terms of Ka or pKa here, right? Now, let us look at the Ka values of some of the aliphatic amines. If you look at ammonia, the Ka value, pKa value is 9.26. Now we said, remember, a basic compound will have high pKa values. Okay? Compared to 9.6 for ammonia, if you go to methylamine, it becomes 10.64. You can see 10.81 for ethylamine, 10.66 for cyclohexylamine. All these values, if you see, all aliphatic amines, that means will be stronger bases than ammonia. That is the first rule that we learn from here, right? From the Ka values, you can see. Okay. Let us now see the next slide. These are the pKa values of aromatic amines. You can see this is aniline. This is para-toluidine. All the pKa values, if you see, these pKa values are lower than that of ammonia. That means what? All aromatic amines are weaker bases than ammonia. Okay, that is the second rule that we learn here. Correct? Now let us discuss the factors which affect the basicity of amines. You can see there are 5 factors which are affecting the basicity of amines. The first of those factors is the inductive effect. We will learn how an electron donating group will increase the basicity of amine and how an electron withdrawing group decreases the basicity of amine. Number 1. Okay. The second case is hybridization on nitrogen that we are talking about. We will find as the percentage S character goes on increasing, that means when you go from an sp3 to an sp2 and then finally to an sp hybridized nitrogen, the S character is increasing, we will see that the basicity will go on decreasing. Okay. With hybridization, percentage S character, the basicity will decrease. The third effect is solvation. The solvation of the corresponding ammonium salt, the conjugate acid of the amine. You will find that higher is the extent of solvation of amine, the corresponding conjugate acid, higher will be the basicity of amine. Please understand one thing. Always there is a rule. For an amine to be strongly basic, the conjugate acid should be stable. Stable, the conjugate acid is, higher is the basic character of the amine. Now we are comparing here the extent of solvation. Higher is the solvation of conjugate acid, Solvation होने से क्या होता, it releases solvation energy, so it is stabilizing the molecule. So higher the extent of solvation of the conjugate acid, higher will be the stability of the amine. All right. Next is the steric effect to solvation. We will find that as the size of R group attached to nitrogen goes on increasing, this R group will increasingly hinder the solvation of the conjugate acid. So, as the solvation of the conjugate acid decreases, the basicity of the amine will decrease. That means in cases where nitrogen is bound to a bulky group, the solvation will be less. So, the basic character will be less. Follow me. And the last point here is resonance. Resonance will come into play more specifically for aromatic amines. We will see how if the benzene ring is offering plus R effect, the basic character will increase. And in case the benzene ring offers a minus R effect, the basic character will decrease. Okay. Let us start. The first case is the hybridization. I will take one example. These are the two nitrogen containing molecules. This compound is called pyridine, and this compound is a corresponding saturated analog of this. ठीक है, इसको reduce करो. If you reduce pyridine, you will get this molecule piperidine. Okay, so you see what is the hybridization on this nitrogen. Here is sp2 hybridized, whereas the nitrogen here is sp3 hybridized. Just now I told you that as the S character decreases, the percentage S character decreases, the basicity will increase. So you find that pyridine should be a weaker base than piperidine, right? Because that is nitrogen with sp3 hybridization, right? The next point is the resonance. So I told you supposing you have aniline. Now, when this lone pair of electrons on nitrogen enter into conjugation with the ring, what will happen? The nitrogen will acquire a plus charge. Now, when the nitrogen acquires a plus charge, it will no longer be basic. So what resonance does? The resonance is actually decreasing the basic character of amines when the lone pair of electron are getting delocalized on the ring, right? This electron pair will get delocalized like this. So you can see because of resonance, the nitrogen has acquired a plus charge and the basic character will decrease because nitrogen is no longer able to give its electron pair, right? Let us see. So here you can see here the lone pair of electron. They overlap with the pi electron pair on the ring and the electron pair gets delocalized. Okay? And this example I have taken just now. Pyridine, nitrogen is sp2 hybridized. You can see the pKb values. Piperidine has a much lower pKb value as compared to pyridine. That shows the higher basic character of piperidine as compared to pyridine. Okay. Now let us talk of the remaining three factors which affect the basic character. The first one of those is the inductive effect. Now, we say that the basic character of a compound is because of its ability to donate electron pair. Now, if the electron charge density on nitrogen increases, its ability to donate electron pair will also increase. So that will increase the basic character. So we say that the plus I effect will increase the basic character and the minus I effect will decrease the basic character because it is decreasing the electron charge density on nitrogen, right? Next is the solvation effect. Now the solvation, I will give you one example. Let us say you have an amine like this. In water, it will get protonated and it will exist as the corresponding ammonium salt, right? Now, this ammonium salt has 3 donatable hydrogens. Okay? So, it can form very, very strong hydrogen bonds with water molecule. Because of the presence of 3 donatable hydrogens, it could form very, very strong hydrogen bond. That means the extent of solvation of this amine will be very high. So higher is the extent of solvation, higher is the solvation energy released, more is the stability of the conjugate acid. So higher will be the basicity of the amine, right? Okay. The next point is the steric effect to solvation. Let us consider 2 different molecules. I have written the corresponding conjugate acid for a secondary amine as well as for a tertiary amine. Now you find that secondary amine has 2 donatable hydrogens, so it will form hydrogen bonds with water molecule at two different sides, whereas the tertiary ammonium salt has only one donatable hydrogen, so it will form only one hydrogen bond. Moreover, because of the bulkiness of the R group, as the R group gets bulky, this bulky R group will prevent the water molecule from approaching the hydrogen. So we say that a bulky R group will exhibit a steric inhibition to solvation. It will not allow the solvation to take place. So as the size of the R group attached to nitrogen increases, the extent of solvation will decrease. So the basic character will decrease. Follow? Okay. Now, having learned the factors which affect the basicity of amines, let us now try to explain the trends of basicity in primary amines first. Okay. I will give you two examples here. I have written, if you see here, secondary greater than primary, greater than tertiary, greater than ammonia. Now, I am writing two examples here on the board. Please concentrate. You see here, in case of methylamines, you find that the order is secondary, greater than primary, greater than tertiary, greater than ammonia, what I have written here. Okay. When you go from a methylamine to ethylamine, what you find is that there is a slight change in order. You see that secondary amine is still most basic, but next comes the tertiary amines, and then the primary amine, and then ammonia. So that means there is something happening here which has led to the change in order. Let us try to understand first this order, why it should be this order, and then we'll see why the order has changed here. Okay? Now, I said especially please remember in case of aliphatic amines, the trends will depend upon three factors, and those three factors are inductive effect, solvation, and steric hindrance or steric inhibition of solvation. Okay? Now please see. If you look at the inductive effect, you find that in case of tertiary amine, there are three alkyl groups attached to nitrogen, and the alkyl group is electron donating. So it is increasing the electron density on the nitrogen. That means you find that as you move from primary to secondary to tertiary amine, the electron charge density on nitrogen is going on increasing. Okay? So it should increase the basic character, and the basic character, if it were only dependent on inductive effect, should follow the order tertiary greater than secondary greater than primary. Right? However, besides inductive effect, we have learned that there are two other factors which are playing very important role. The second of those factors is the solvation effect. Let us see. Let us write the structures for solvation. This is the solvation of the quaternary salt for tertiary amine. This will be for the secondary amine, and for primary amine we had written earlier also. These will be the structure for the solvation of the tertiary, the secondary and the primary amine, right? You can see that the extent of solvation is progressively increasing as you go from tertiary to secondary to primary. Mind you, the extent of solvation is governed by the size of the cation. Smaller is the size of the cation, higher will be the extent of solvation. Now, a primary amine cation, the corresponding ammonium salt will be the smallest in size. That is why it is most extensively solvated, right? So, because the extent of solvation in primary amine is most, the basic character of primary amine should be highest if it is only governed by solvation. Okay? So based on solvation, the order will be primary greater than secondary greater than tertiary. So you can see that inductive effect के ऊपर the order is, so a resultant of these two factors is that the basicity of secondary amine becomes the highest. So invariably in case of aliphatic amines, secondary amine will be most basic. Okay? Now we have to decide between the primary and the tertiary amine, right? When the alkyl group is small, okay? The small alkyl group does not show any steric inhibition to solvation. Okay, like methyl group, there is no steric inhibition to solvation. So that means the solvation effect will predominate over the inductive effect. Right or not? Because there is no steric inhibition to solvation, that means solvation is very important factor. So if solvation is an important factor between primary amine and tertiary amine, which will be most basic? Primary amine will be most basic. So in cases in those amines where there is no steric inhibition to solvation, primary amine will be more basic than tertiary amine. Okay? So that is why the order here. Secondary, then primary, then tertiary, and in the end there is ammonia. Clear? Now, in the second case, when you move from a methyl group to an ethyl group, the size of the group is increasing. Ethyl group is bulkier. So the bulkier ethyl group offers steric inhibition to solvation. So because of which what happens is solvation is no longer the predominant factor. That means wherever you have steric inhibition to solvation, the basicity will be decided on the basis of inductive effect. Now, if inductive effect is the deciding factor between tertiary amine and primary amine, which will be most basic? Tertiary amine. So, in those cases where you have steric inhibition to solvation, the order will be secondary, greater than tertiary, greater than primary, greater than ammonia. Very clear? Okay. Next, let us go to the basicity of aromatic amines. Now, the first thing we have to understand is we have seen the pKa values and we have learned that rule that aromatic amines are less basic than ammonia. And if you remember the Ka values, you will also say that aromatic amines are less basic than aliphatic amines. Right or not? So, first thing that we will like to learn is what makes aromatic amines less basic than ammonia, number one. And then we will see what are the factors which affect the basicity and how it affects the basicity. Okay? So please remember, there are three factors which are responsible for the decreased basicity of aromatic amines as compared to aliphatic amines. What are those three factors? The first factor here is the resonance, because of which the lone pair of electron on nitrogen get delocalized. Okay. The second factor is the sp2 hybridization of the ring carbon as compared to sp3 hybridization of the carbon in case of the aliphatic amines, right? Now please take the example of aniline and compare it with methylamine. This carbon is sp3 hybridized, whereas this carbon here is sp2 hybridized. So an sp2 hybridized carbon is more electronegative. So it will pull the lone pair of electrons more strongly towards itself. That is why the second reason for decreased basicity is the sp2 hybridization of the ring carbon. Okay. And the third factor is the stability of anilinium cation, the conjugate acid, as compared to that of aniline. Now please see the resonance structures. We have written it earlier also. Because of resonance, we have learned that nitrogen is carrying a positive charge, so the basic character is decreasing. How many resonance structures can you write for aniline? There are 5 resonance structures that one can write for aniline. But try writing the resonance structures of anilinium cation. How many resonance structures will you be able to write for anilinium cation? You can write only 2 resonance structures for anilinium cation. Those are the 2 calculus structures, right? Now, because there are no lone pair of electrons, there is no resonance with the ring. Because of which you can only write the 2 canonical forms. Okay? So that means higher the number of canonical forms, higher is the resonance energy released, higher is the stability of the molecule, right? So since aniline can be depicted as a resonance hybrid of 5 structures, the resonance energy release will be higher than anilinium cation, which can only exhibit 2 resonance structures. That means the stability of anilinium cation is less as compared to aniline. So if the conjugate acid is less stable, the basicity will be decreased, right? So the third factor which makes aniline a weaker base is the decreased stability of anilinium cation. Follow? Okay. So having learned that, let us see what the substituents will do to the basicity of amines. There are 2 rules which you should remember. And what are those 2 rules? Number 1, if you have an electron donating group, it will increase the basicity of amines. And if you have an electron withdrawing group, it will decrease the basicity of amines. Okay? What are the electron donating groups which are attached to benzene ring normally? Electron donating groups are like OH, OCH3, right? And what are the electron withdrawing groups which are attached? You have Cl, you have NO2, you can have Cn, you can have CHO, you can have COOH, so many. They're all electron withdrawing groups, right? So an electron donating group is going to increase the basicity and an electron withdrawing group is going to decrease the basicity. Let us first understand why it is happening before we go to the specific examples. Now please understand. sp2 hybridization will remain same irrespective of the nature of the substituent. So when you are considering the basicity of aromatic amines, sp2 hybridization will not come into play. sp2 hybridization comes into play only when you compare aliphatic and aromatic amines, right? So the 2 important factors which we have to keep in mind when we are comparing the basicity of aromatic amines amongst themselves will be resonance of aniline and the stability of anilinium cation, right? Again, if the extent of nitrogen lone pair delocalization increases, the basic character will decrease. Okay? And if there is anything which is preventing the lone pair of electrons on nitrogen from entering into resonance with the ring, it will increase the basic character. Okay? So if you have an electron donating group, what it will do is, it is increasing the electron charge density on the ring. Because it increases the electron charge density on the ring, it is preventing the lone pair of electron on nitrogen from entering into resonance with the ring. So the basic character will increase. Okay? There will be a decreased tendency for this lone pair of electron in case of an electron donating group to enter into resonance with the ring. That means extent of positive charge on the nitrogen will decrease. So the basic character of amine will increase. Right? What about stability of aniline cation in case of an electron donating or an electron withdrawing group? Now, in case you have an electron withdrawing group, it is going to increase the electropositivity of the nitrogen. That means it will increase the positive charge on nitrogen. If it is increasing the extent of positive charge on the nitrogen, means it is decreasing the basic character. Okay? So, an electron withdrawing group is further destabilizing the aniline cation by increasing the electropositivity of the nitrogen. Okay? So, that is why it will decrease the basic character. Okay? On the same lines, if you have an electron donating group, it is going to decrease the extent of positive charge on the nitrogen. So an electron donating group, because it is decreasing the extent of positive charge on the nitrogen, it will increase the basic character. So now you understand how electron donating or electron withdrawing group is affecting resonance and how they are affecting the stability of aniline cation. Okay? One more point I want to tell you before I take specific example. We'll come back to this later. And that is ortho effect. Now you have studied ortho effect when you were studying the acidity of aromatic carboxylic acid. Please recollect, you have learned that ortho substituted carboxylic acids are stronger acids than the para substituted because of ortho effect. What is ortho effect? Ortho effect is nothing but a combination of steric factors and the electronic factors. When you apply that same rule to amines, we find that ortho substituted amines will be weaker bases irrespective of the nature of the group. So please remember, ortho substituted carboxylic acids are stronger acids irrespective of the fact whether they are electron donating or electron withdrawing. And on the same lines, ortho substituted amines will be weaker bases irrespective of the fact whether they are electron donating or they are electron withdrawing. Okay? Now what we will do is, we will be taking specific examples to justify the order of basicity as observed in aromatic amines. Okay? The first case is the electron donating group. Here I have taken example of the donating group being a methoxyl group, or next case we will take hydroxyl group. Now both these groups are such that the plus R effect in these cases is much stronger than minus I. They have both plus R and minus I, but their plus R is much stronger than minus I, right? So the OH and the OCH3 group, they offer both plus R and minus I, but in this case the plus R is stronger than minus I. That means they are ring activating. They are acting as electron donating group. So that means they will increase the basicity. So what you find is that the hydroxyl or methoxyl substituted aniline will be a stronger base than aniline. Because it is ring activating, right? So let us see the order in those two cases and then we will justify the order. In case of hydroxyl group, there is a slight change. Yes. Oxygen है ना? Oxygen is electronegative. Because it is electronegative, it will withdraw electrons. So कोई भी oxygen substituent है वो minus I effect तो होगा बेटा. ठीक है? That you cannot rule out because carbon oxygen में oxygen is more electronegative. So electrons so it will withdraw. Though it is a weaker effect because plus R effect is strong. इसीलिए we say they are activating groups because plus R is stronger than minus I. ठीक है ना? Now let us justify this order first. Now please understand, when you have these groups present at ortho or para position only, they can donate electrons by resonance. At meta position, there is no resonance. Plus R effect nahi hai. At meta position, you have only minus I effect. Okay? So because at meta position, they are only electron withdrawing, they will be least basic, right? Only minus I. There is no plus R, right? We have just now said that OCH3 or the OH group, they donate electrons by resonance. Okay? Let us write the resonance structure. And understand how they are increasing the basic character. Now what you see is because of resonance, what is happening is this nitrogen, the carbon which is attached to nitrogen is acquiring a negative charge. Because you can see here in this particular structure, because the negative charge is coming on this carbon, this negatively charged carbon will prevent the lone pair of electrons on nitrogen from entering into resonance with the ring. That is how it is increasing the basic character. Follow me? So you agree that para substituted This compound is called anisidine. OCH3 when you put to benzene ring is anisole, right? And this compound is called anisidine, obtained from anisole. So because it is present at para position, the inductive effect will be minimum because the inductive effect decreases as the distance increases, right? So minimum inductive effect plus resonance will make it most basic, right? Now to understand why aniline has come before orthoanisidine. This will be para-anisidine? Yes, because at ortho position you have ortho effect. Because of ortho effect, the ortho-anisidine will become a weaker base than aniline. Okay? So here you have ortho effect operating. Okay? But then the question to be answered is कि अगर ortho effect है, so then it should be least basic. But at ortho position it also has plus R effect. Please remember that. Which is not there at meta position. Meta position only electron withdrawing hai. Ortho position you have ortho effect, but you also have plus R effect. The resultant of that is that it makes orthoanisidine more basic than the meta-anisidine. Follow my point. Okay, beta. Now, the question to be answered here is that we have understood everything here. And now why the order has changed here? This is because there is something else operating here which is not possible here. What is that? Hydrogen bonding. Hydrogen bonding of what? The conjugate acid. In case of orthohydroxyaniline, this compound is orthohydroxyaniline. The conjugate acid will be stabilized by intramolecular hydrogen bonding. Because of the stabilization of conjugate acid by intramolecular hydrogen bonding, the basicity of orthoaniline is more than that of aniline in spite of ortho effect. Even though ortho effect is operating, but the conjugate acid is becoming highly stable because of intramolecular hydrogen bonding. That is why orthohydroxyaniline will be a stronger base than para-hydroxyaniline. Have I made myself clear? Next, one example we will take for electron withdrawing group. If it is an electron withdrawing group, that means it is ring deactivating. And if it is ring deactivating, it will decrease the basicity as compared to aniline. That means aniline will be a stronger base than all those substituted anilines where you have a electron withdrawing group attached to ring. So aniline will come first. Here I have taken example of ortho, meta, para chloroanilines. Okay? Now please understand, in case of fluorine, they are groups where they have plus R effect and they have minus I effect, but very importantly, the plus R effect is much weaker than minus I. That means the predominating factor is minus I effect. And the inductive effect, it decreases with distance. That means para-chloroaniline, the inductive effect will be least. So it will be most basic, followed by meta and then ortho. Okay. So that will be the order of ortho, meta, para, chloroaniline. If okay, now if you have nitroanilines, then what will happen? नहीं बेटा, nitro में there is one difference. No. This will be the order that you will observe in case of nitro compounds. Now please understand, nitro group mate has strong minus I and strong minus R. ठीक है? At meta position you have only minus I. So least ring deactivating है ये. That is why meta nitroaniline will be most basic amongst the ortho meta para nitroanilines. ठीक है? Then you have para and then you have ortho. Ortho least क्यों है? Ortho effect है because वहां पे, right? Otherwise, at ortho and para position, you have both plus R and minus R and minus I both operating. So the ortho effect makes ortho substituted aniline less basic than para substituted aniline. Okay. The basicity of aryl alkyl amines. Now, when benzene ring is not directly attached to nitrogen, so you have aniline here, benzene ring is directly attached to nitrogen. In this case, aryl, this is benzylamine. Benzene ring is not directly attached to nitrogen, so it cannot offer minus R. Huh? So if it is not offering minus R, but it can offer minus I, it is a weak minus I effect. So because there is no minus R here, the lone pair of electron will remain on nitrogen. There is only a faint minus I, which will make benzylamine a stronger base than aniline. ठीक है बेटा? Next is the basicity of N substituted anilines. You see that what is the structure? The structure is like this. This is a tertiary amine. Huh? Now why? In case of aliphatic amines, we had learned that secondary amine is most basic. In case of tertiary amines, aromatic amines, we are saying that the tertiary amine is most basic. The reason here is in case of aromatic amines, the most important factor which governs the basicity is resonance. Okay. Now, when there are two alkyl groups attached to this nitrogen is no longer in the same plane as this carbon. For the lone pair to get delocalized, the nitrogen and carbon should be in same plane. So because of the two bulky R groups, the nitrogen is no longer in the same plane as carbon. So the lone pair of electron cannot enter into resonance with the ring. If it is not entering into resonance with the ring, means the basic character is increasing. So we say that the N substituted anilines are stronger bases than aniline because of steric inhibition to resonance. Okay. देखो प्लस आई इफेक्ट तो है यहाँ पे, R group है दो, प्लस आई इफेक्ट तो होगा, but plus I effect is not the very important factor. What is the important factor is steric inhibition of resonance, because of which the lone pair of electron will reside on nitrogen. Okay? So that is why in case of aromatic N substituted amines, the order will be tertiary greater than secondary greater than primary, right? Because in primary there is no steric inhibition of resonance. Acha, okay. Now look at the last trend. Now what has happened? Just now we said that tertiary amine should be most basic if the R groups are alkyl. But please remember, aryl group offers minus R. As the number of aryl groups attached to nitrogen increase, the lone pair delocalization will increase. देखो aniline में the lone pair are getting delocalized only on one benzene ring. In diphenylamine, they are getting delocalized on 2 benzene ring. And in triphenylamine, it will get delocalized on 3 benzene ring. That means the electropositivity of nitrogen goes on increasing, right? So the basic character will decrease as you move from aniline to diphenylamine to triphenylamine. Follow me? So अगर alkyl substituted anilines हैं तो वहां पे steric inhibition to resonance है तो tertiary amine will be most basic. If aryl amines हैं then as the number of aryl group increase, electropositivity of nitrogen is increasing, so basic character will decrease. So in that case, aniline will be most basic. Clear with everybody? Okay. Let us now go to the methods of preparation of amines and the diazonium salts. There are 9 different methods of preparation that we are going to discuss. First is the Hofmann's ammonolysis. Next will be the alkylation of azides. Third will be reduction of nitro compounds. Fourth will be reduction of nitriles or amides. Fifth will be reduction of oximes. Sixth will be phthalimide synthesis. And the seventh will be reductive amination of carbonyl compounds. Then would be Hofmann degradation and the Schmidt reaction. And finally, one method for preparation of diazonium salts, and that will be the diazotization reaction. Okay, let us start with the first method. That is the alkylation of amines, alkyl halides. This reaction is called the Hofmann ammonolysis. Now please see here. Hofmann ammonolysis is nothing but an example of a nucleophilic substitution reaction, right? Where the halogen will be replaced by an amine in alkyl halide. Okay? If you have alkyl halide reacted with ammonia, you will have the primary amine being formed. But please understand that this reaction will not stop here. This reaction does not stop here. Once the primary amine is formed, it will further react with alkyl halide and you will get a secondary amine which will further react with alkyl halide. You will get tertiary amine which will further react with alkyl halide. You will get the quaternary salt. So that means the Hofmann ammonolysis is not a very good method to synthesize amines. What is it doing? It is converting an alkyl halide to amine. Yes, but you are getting a mixture of amines, so not a very good method to prepare amines, number one. The second thing is you cannot prepare aryl amines by this method because the aryl halides do not undergo nucleophilic substitution reaction. ठीक है? So आप bromobenzene से aniline नहीं बना सकते on reaction with ammonia because it is not easily undergoing nucleophilic substitution reaction. Those are the two drawbacks of the Hofmann ammonolysis reaction. Okay? Another method to convert alkyl halide to amines is by reaction with azides. What you do is you react alkyl halide with sodium azide or potassium azide and you convert it into alkyl azide and then do the reduction with lithium aluminium hydride or H2 catalyst. Any of these you can use, you get the corresponding amine. The advantage of this reaction is that the alkyl azides are not nucleophilic. See, here you have primary amine which reacts further with alkyl halide to give you secondary, then tertiary and then quaternary. The alkyl azides are not nucleophilic. That means you will not get a mixture of amines being formed. You will only have the primary amine being formed. Okay? But there is one disadvantage of this reaction. And that disadvantage is that the alkyl azides are toxic in nature. Okay? So their use should be avoided. Though a good method to convert alkyl halides to amines, the disadvantage is that the alkyl azides are okay. So we have you can see how benzyl chloride has been converted into benzylamine by doing the azide synthesis. Okay? So the overall reaction is conversion of alkyl halide to the corresponding amine. Okay? The next reaction is reduction of nitriles and amides. Now nitriles, if you see here, how do you prepare nitriles? You can prepare nitriles from alkyl halide, right? Alkyl halide, if you react with sodium cyanide or potassium cyanide, you will get the corresponding alkyl nitrile. Those alkyl nitriles you can reduce with lithium aluminium hydride or with sodium in alcohol where it is called the Mendius reduction or with H2 catalyst. So important point to remember in this reaction is you are converting alkyl halide to amine having one carbon more. See, alkyl azide reaction, you converted alkyl halide to amine having same number of carbons. By this reaction, you have converted alkyl halide to amine which has one extra carbon, right? So it can be used as a conventional step-up reaction in the organic chemistry reactions, right? Similarly, if you have a carboxylic acid, what will happen when you react with acid thionyl chloride? You get acid chloride, right? And when you react with ammonia, it will form the corresponding amide, right? Reaction किया है ना आपने acid chloride, you react with thionyl chloride, you get acid chloride. And acid chloride, when you react with ammonia, it forms acid amide. So the amide, when you reduce with lithium aluminium hydride, it again forms corresponding amine. So that means reduction of amides with LAH offers a method by which you can convert carboxylic acid to the amines having same number of carbons. That is how, if you remember, it is easier to remember. Carboxylic acids converted into amines having same number of carbons, alkyl halides being converted into amines having one carbon more. Right? The next is reduction of nitro compounds. Now, reduction of nitro compound can be used as a method for both preparation of aliphatic as well as aromatic amines. Okay? In fact, it is a very good method to prepare aromatic amines because aromatic amines you can't prepare from aryl halides. So the easiest method to prepare aromatic amines is to reduce the corresponding nitro compound. Follow me? Now the reduction of nitro compounds can be done in three different ways. First is by hydrogenation with H2 catalyst. So if you have nitromethane, right, I can reduce it with H2 palladium or platinum and convert it into corresponding amine. That is one way of carrying out the reduction reaction by hydrogenation. The other way of doing the reduction is in the acidic medium when you use metal acid. Okay, you can use tin HCl or you can use tin chloride HCl or you can use zinc HCl. Any of these reducing agents will reduce the nitro compound to corresponding amine. Okay? Another third way, both these methods can be used for aromatic as well as aliphatic amines, right? But the third method the reduction with lithium aluminium hydride can only be used for aliphatic amines. In case of aromatic nitro compound, you get diazo compounds. So it cannot be used to prepare aromatic nitro amines. Okay. So we say only for aliphatic molecules. Follow? So अगर बेंजीन से एनिलीन बनाना है तो रूट वुड बी टू कन्वर्ट इट इनटू नाइट्रोबेंजीन एंड देन रिड्यूस इट. ठीक है? So you can convert aromatic hydrocarbons to aromatic amines by this method, right? Next is the reduction of oximes. How do you prepare oximes? The oximes are prepared from carbonyl compounds. Carbonyl compound, when you react with hydroxylamine, they will form oxime, right? We have learned this reaction when we did the carbonyl chemistry. So this oxime can be reduced with either lithium aluminium hydride or sodium in alcohol to form the corresponding amine. Basically, what is happening in this reaction is, again, we are converting C double bond O to CHNH2 via oxime. पहले कार्बोनिल कंपाउंड को ऑक्साइम में कन्वर्ट किया and then we have reduced it to the corresponding amine. So this offers a method of converting C double bond O, the carbonyl compound, to amine having same number of carbons. Okay. Right? Next is the Gabriel phthalimide synthesis. The phthalimide synthesis is the best method to prepare the primary aliphatic or the aryl alkyl amines. Again, it cannot be used to prepare aromatic amines. Okay. There is no mixture formation like in case of Hofmann homolysis. There is no toxicity involved like in case of alkyl azides. That is why Gabriel phthalimide synthesis is the best method to prepare primary aliphatic or the aryl alkyl amines. Is that okay? What is Gabriel phthalimide synthesis? You see, this is phthalimide. This hydrogen is acidic, right? When you react with KOH, what happens? Hydrogen is replaced. You get the potassium salt, and this potassium salt, when you react with alkyl halide, again nucleophilic substitution reaction is taking place, right? And when you do the hydrolysis of this N-substituted amide, you can do hydrolysis with acid or you can do hydrolysis with alkali. what will happen? Bond will cleave here. Okay? And you will get the corresponding amine being formed. And this portion will form the phthalic acid. All right? Next is the reductive amination of the carbonyl compounds. Now, just now we have learned that carbonyl compounds you can convert to oximes, and those oximes you can reduce to corresponding amines. That is a method by which you can convert C double bond O to CHNH2, right? To corresponding amine. This is another method by which you can convert carbonyl compounds to amine. But this is a more versatile method in the sense, by this method you can prepare all the three categories of amines. You can prepare a primary amine, you can prepare a secondary amine, as well as you can prepare a tertiary amine. Oximes say you can only prepare a primary amine. Okay? That is the advantage of this reductive amination reaction. So how this reaction takes place? You take a carbonyl compound, react it with ammonia in the reducing medium. You can use H2 nickel, or you can also use sodium cyanoborohydride. Any of these reducing agents can be used. What happens in this reaction is, if you have a carbonyl compound like say acetone, okay, and I reacted with ammonia. This reaction we have learned in carbonyl chemistry, you will get the corresponding imide being formed. Right? Now, but you have reducing medium. Because there is hydrogen present, this imide will be immediately reduced. To the corresponding amine. Okay? So, if you start with ammonia, you have ended up with a primary amine. If I replace this ammonia with primary amine, my product will be a secondary amine. And if I start with a secondary amine, my product will be a tertiary amine. So you can see how by suitable amine, I can prepare all the three categories of amines by doing the reductive amination of carbonyl compounds. Okay? The next is the Hofmann-bromamide reaction, which is called the Hofmann degradation reaction. Now, the Hofmann-bromamide reaction is a conventional step-down reaction used in the organic chemistry. Basically, it is used to convert carboxylic acid or the acid amide to an amine having one carbon less. You have carboxylic acid or you have acid amide, you can convert it into amine having one carbon less. How does the reaction take place? You can see here. If you have amide, you know this amide can be prepared from carboxylic acid, right? That is why I said carboxylic acid or acid amide, because amide you can prepare from carboxylic acid, right? You have amide, you react it with bromine in NaOH, sodium hydroxide or potassium hydroxide. The only thing that you have to do here is, you have remove this CONH2 and join NH2 group to R. So you get the corresponding amine. That means if I start with benzamide, my product will be, if I start with benzamide, what will be my product? And I do Hofmann degradation reaction. I will get aniline, right? So you NH2 निकाल के just put NH2 group. That is the product you will get. Next is the Schmidt reaction. Schmidt reaction is similar to Hofmann degradation. Same concept. You have carboxylic acid. It is converted into amine having one carbon less. You have reaction taking place with this compound HN3 that is called hydrozoic acid in sulfuric acid. Right? So again, just remove this COOH and replace it by NH2. That's how you get the product. Okay? So if I start with benzoic acid, reacted with hydrozoic acid in concentrated sulfuric acid, my product will be again aniline. All right. ठीक है बेटा. The last reaction is the diazotization reaction. This is a reaction which is used to prepare the diazonium salts. Right? How do you prepare diazonium salt? If you have aromatic amine and you react it with sodium nitrite in HCl, the important thing is that the temperature should not exceed 5 degrees. The temperature should be between 0 and 5 degrees. React aniline with nitrous acid in sulfuric acid at temperature less than 5 degree and you will get the corresponding diazonium salt. Okay, this reaction is called diazotization reaction. Okay, so these are all the methods for preparation of the amines and the diazonium salts. Now what we will do is we will take up some questions based on what we have done today. Okay. Let us look at the first question. It says, how classification of amines is different from those of alcohols? Can you tell me? No. No. How do you classify primary, secondary, tertiary alcohols? It is based on the nature of carbon to which OH is attached. Okay? If the carbon is primary, the alcohol will be primary, right? We have a secondary carbon here, the alcohol becomes secondary. Whereas in case of amines, it is the number of R groups which are attached to nitrogen, right? Clear? Okay. See the next question. It says tertiary butyl amine cannot be prepared by the reaction of tertiary butyl bromide with ammonia. What is this reaction? This is Hofmann ammonolysis. Why so? We said that Hofmann ammonolysis is reaction of alkyl halide with ammonia to give corresponding amine. But the important difference here is that amine alkyl halide should be preferably primary. Okay? Because this is a tertiary alkyl halide. So it will undergo an elimination reaction. Because of elimination reaction, there will be no substitution taking place here. You will have elimination reaction taking place. Hydrogen will be lost from this carbon and Br from here, and you will get dehydrohalogenation taking place here, and it will give you isobutene, right? Okay, so please remember Hofmann ammonolysis is suitable if you have alkyl halide is primary or at most secondary, never for tertiary amines. Okay, because you will have elimination taking place in that case. The third question is Can you prepare aniline by phthalimide synthesis? Can you? No, you can't, because we said that phthalimide synthesis can be used only for aliphatic or aryl alkyl amines, because if I have to prepare aniline, I will have to react it with bromobenzene or iodobenzene, and which do not undergo nucleophilic substitution reaction. So aromatic amines cannot be prepared from phthalimide synthesis. Correct? Now, next is you have to you have to carry out these conversions. Let us see how you will do. Cyclohexanol to cyclohexylamine. Please write the structure of cyclohexanol. It is important that you get friendly with the common names of organic compounds, because only if you are able to write the structure, you will be able to carry out the conversion. The conversion is very easy, but if you don't know what is the structure of cyclohexanol, how will you do the conversion? Okay, so please try to name the organic compounds both by IUPAC nomenclature and common name whenever you do an organic reaction practice. Okay. This is cyclohexanol. हाँ, सिंपल कन्वर्शन है ये तो. See, amongst the so many routes that we have discussed for synthesis of amines, we said that amines can be prepared by reaction of alkyl halides with sodium azide. We will rule out Hoffman ammonolysis because it is a very poor method. Okay? Or we can do phthalimide synthesis. That is the best method to prepare amines from alkyl halides. So what you do is you convert it into alkyl halide. How will you convert alcohol to alkyl halide? PBr3, PCl5, है ना? SOCl2, anything you react? बन गया? Now you do the either phthalimide synthesis, or you can react with sodium azide. You will get cyclohexyl azide being formed, and this when you reduce with lithium aluminum hydride, you will get cyclohexylamine being formed. Correct? Let us do the next one. N-hexane nitrile to 1-aminopentane. So immediately you should spot one thing. What is that? There is a step down reaction taking place. And we have learned one reaction to do step down. That is what reaction? Hoffman bromamide. So what you do is you convert this nitrile to amide and then do Hoffman bromamide. How will you convert nitrile to amide? Very good. So you do partial hydrolysis, right? And now do Hoffman bromamide. ठीक है ना? So you have converted a 6-carbon molecule to a 5 carbon molecule, right? Okay. ठीक है ना? Let's go on to the next question. Boiling point of normal propyl amine is more than trimethylamine, even though both have comparable, it should not be melting point, molecular masses, it should be. Melting point नहीं हो सकता, it has to be molecular masses. है ना? Normal propylamine is a primary amine. So there are 2 hydrogens attached to nitrogen. That is a tertiary amine, trimethylamine. There are no hydrogens attached to it. So there is no hydrogen bonding. That is why the boiling point of N-propylamine will be higher than that of trimethylamine. Next question, please. Amines are stronger bases than alcohols. See, I told you basicity depends upon the ability to donate electrons. A molecule which can easily donate electron will be a stronger base. Now, what is the difference between an amine and alcohol? Is the presence of the heteroatom. Oxygen is more electronegative, so it cannot easily give its electron pair. That is why it will be a weaker base. The alcohols are weaker bases because of the higher electronegativity of of oxygen as compared to nitrogen, right? Oxygen is more electronegative. ठीक है बेटा? The next question is, you have to arrange the following into the increasing order of basicity. That's why I told you should remember these 3 molecules, because this type of question frequently comes in the IIT entrance, okay? Okay. Now, obviously, you can understand that piperidine will be most basic, है ना? Because nitrogen is sp3 hybridized here. Okay. Between these two, what happens here is, this is pyrrole. This is an aromatic compound. What happens is, the lone pair of electron, they enter into resonance with the ring. Because they are entering into resonance with the ring, what will happen? The nitrogen will acquire a plus charge. So you can see that because the nitrogen is acquiring a plus charge, the basicity of pyrrole will decrease. Okay? If you write pyridine resonance, what happens is, the resonance happens like this. In case of pyridine, what is happening is, because of resonance, nitrogen is acquiring negative charge. So pyridine will be more basic than pyrrole. So that means If I say this is 1, this is 2, this is 3, then 3 will be least basic, then 2, and then 1. So that will be the order of basicity of these compounds. ठीक है बेटा? Can we go to the next slide? The next question is that amides are more acidic than amines. Let us write the structure quickly and understand what will make amides more acidic than amines. Now you have learned that in case of amides, you can have resonance, and because of resonance, what will happen? The lone pair of electron will get delocalized, and because of that delocalization, nitrogen will acquire a positive charge. So if nitrogen is positively charged, the basic character will be less, right? So basic character is less means acidic character is more. So that makes amides more acidic than amines, right? I think we have time for one last question. Let us take the first part. You have to arrange in the increasing order of basicity. Quickly write down the structures in the first part, A part. Okay, so do you have the answer? Will be most basic. Steric inhibition to resonance. Right? Steric inhibition to resonance. Then followed by paratoluidine, because methyl group is electron donating. It donates electrons by hyperconjugation as well as by inductive effect. Okay? Alkyl groups to ring donate electrons by both hyperconjugation as well as inductive effect. Right? Then aniline, then paranitroaniline, because nitro group is electron withdrawing, so it will be least basic. Okay? So the order will be correct. Let us do the next part. Write down the question. Now please see. First two are aliphatic amines. Okay. They are more basic than aromatic amines. So let us first consider the aromatic amines. Between this and this, N-alkylamine is more basic than aniline. We have learned because of steric inhibition to resonance. Okay? So, aniline will be least basic, then followed by N-methylaniline. Okay? Now, between dimethylamine and methylamine, this is a secondary amine and this is a primary amine. Secondary amine we have learned is more basic than primary amine. So, next will be primary amine. And in the end will come the secondary amine. Okay? The third part should be easy. You should be able to do it very quickly. Let us have the answer now. Please write down and tell me the order. Just remember that aromatic amines are less basic than ammonia, right? Let us write. No, 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 no. Now, beta, diethylamine, then very good. First diethyl and then triethyl. We learned that inductive effect is more important here than solvation, right? And then ethylamine, then ammonia, and then aniline. Okay. I think that will be all for today. In the next class, we will learn the chemical properties of benzene, amines, and the diazonium salts. Okay. Thank you.
Good afternoon, girls. So yesterday we finished indefinite integration. So you must have practiced all the questions, right? And did you see the IIT JEE questions? You were able to handle it, right? So it means that you are fine with it. So the basic concepts clear, right? So now yesterday only we shifted from the indefinite integration to the definite integration, and we saw that it's totally a different ballgame, right? And it was like indefinite was a class of function, and definite was talking about a numerical quantity. Okay, and then we defined definite integration as a machine which calculates the signed area, and then we understood what does it mean when we say signed area, and what does it mean when we say area, and what does it mean when we say area of a polygon and area of a circle. And the moment we say the area of a circle, of area of a unit circle is pi, we are actually secretly using what? The limit, right? We are secretly using the language of limit. And then we see, okay, there is a relation between area, limits, geometry, and the definite integration, right? Then after that, we saw that, okay, using the limit concept, we can go for the summation part. So we saw the big sigma thing, right? And then we broke our curves into various rectangles, and then we summed it up using the concept of limit and the summation, right? And then we were able to derive Riemann's left hand, that was underestimating, and then Riemann's right hand, that was overestimating. And after that, we defined it totally. What does it mean when I say AB fx dx is equal to limit and approaching infinity into that Riemann sum, right? So after that, it was we solved some questions, and then we saw that it's very messy, it's very ugly to solve this way. So we were trying to find a better way. It happened in differential class as well. Initially, when we started differentiating, it was like by first principle. It used to be very messy. It used to be very lengthy, right? So, but time we learned various rules and things became easy. Similarly, for this also, we tried to define accumulation function. You know what was accumulation function? It's very important concept, the accumulation function concept. It was it was basically talking about the if you have a function in yt plane, there is a yt plane, and when you see that when you increase x, if ft is positive, you see ax is increasing, right? And you see a prime x is positive. So you saw there is a link between ft and a prime x. And similarly, when ft was negative, you saw ax is decreasing, so a prime x was negative, right? And then what we did, we tried to define that, okay, fine, we saw a relation between the antiderivative and the differentiation of accumulation function. Then what we did, we said that, okay, I'm going to define fx as a to x ft dt, right? And then I'm going to say that my fb is nothing but a to b ft dt, right? And then we said that fa is nothing but a to a ft dt, which is nothing but 0. And then we said that, okay, there is a function gx whose g prime x is fx. And we also know that this is also f prime x, right? And then using this concept, we said that, okay, my fx is nothing but gx plus c. And we knew that fa is nothing but 0. So we said that fa is nothing but ga plus c, which means c is equal to minus ga, right? So we saw that fx is nothing but gx minus ga. And then we said that fb is nothing but and this was the whole game, right? And this is what you have been exposed to, right? So you understand how the pattern is coming, how things are, we are arriving to the things, right? So the basics is clear, how things are building up. Now, this part, f prime x is fx. We haven't proved it yet, but we can say that f prime x is nothing but a into x plus h ft dt minus a x ft dt upon h. Done? ये बात सबको समझ में आता है? Okay. Should I rub the rest part? Now, I'm going to tell you one inequation regarding the regarding the definite integration. It means m into b minus a Have you seen this inequation before? No. Where m is minimum value of fx, m is maximum value of fx, the interval AB. Now I think it's pretty clear for you that this inequality is true. Why? Because I see this is an area thing, and I have seen the maximum point of this into the width. Obviously, this will be greater than the area or equal to, and this will, and the minimum point into the width. Understood? So the area will lie somewhere between this rectangle and this rectangle, right? Area. Understood this or not understood? Okay. Now, see here. What does it mean? F prime x is nothing but x into x plus h ft dt upon h. Right? Can you see this? So can I say m x plus h ft dt upon h is equal to m? Can I say this? Okay. Now h is approaching 0. Now you understand that if I call this is my curve, and if I call this is my A point, let's say this is YT plane. Okay. So I call this point as x, and I go beyond plus h. So this becomes x plus h. So this is the curve. What will be the minimum and maximum point when limit is approaching 0? It will be equal, and that will be equal to. So m is equal to fx it is greater than this and smaller than this, and both are equal. It means it is also equal to this. So hence we can say that this is equal to. So everything is clear now. No formula is now known to you. The concept is cleared. All the formulas is making sense now. Nothing is coming out of the box, out of somewhere we don't know, right? Everything is understood now. So if anybody asks you what is AB fx dx, the definition using the Riemann sum, and then FB minus FA, the Leibniz rule, and you know how it is coming. The concept is accumulation function. The idea is more important ki how we are arriving to the thing, because I'll show you some questions jahan pe we have to really think of this way, right? So why shouldn't we think everything this way? Okay, clear? Should I rub this? So this was all we did last time, right? Okay, now first thing, we are going to talk about the properties. We know what is the integration, what does it mean, and now we are going to talk about its properties. If I say the first third ka part A, I say A B fx dx is equal to A B ft dt. This is simply finding the area of yx plane, and it is finding the area of yt plane. No issue with it. The area will remain same. Both are numerical quantities. So we are not more interested whether you put x or z or t or ka or kha, whatever, right? So things will be, the property A should be this. It's making sense now? Okay. So first property is clear. The second property you have already understood. A to A fx dx. What will be the area? 0. Right? Third, I see A B fx dx, A C fx dx plus C B fx dx. Okay, it doesn't matter whether C is lying in the between or outside, but A to C the function should be, B to C should be, that should be, the basic should be clear. So it's just finding the area between x is equal to A to x is equal to B line. Even if I go x is equal to A to x is equal to C, I'm coming back. And we are talking about the signed area, right? The convention we know, when we are above and going from left to right, it is positive and it is negative when we are going from left to right. And when we are going from right to left, the above thing is negative and below thing is clear. We are against, that is the convention of sine rule, and it's making sense now. Okay, because this is a decreasing, accumulation function is decreasing, so with x it has to increase. Clear? Done? Should I rub this all three? So these three properties are very important, so please note it down. We are going to chain it up, all the properties together. So you should note down, it is not necessary that C should be between A and B. But what is important, that A to C it should be continuous and B to C it should be continuous. Getting? Now the next thing is A to B fx dx is equal to minus of B to A fx dx. We have already discussed this. So this is pretty clear. You know, understand the sign thing. If you're going from left to right, you're above, positive. If you're below, negative. So you must understand low to high. Then high to low. Okay. And if you're down, going from high to low, you have to replace it. So you understand the relation? Either way, it's right? Okay. So you understand the convention. Above thing is positive if you are going from left to right. Below thing is negative if you're going from left to right. If you're going from right to left, above thing is negative. Below thing is positive. Clear? Okay. The next important property is A to B fx dx is equal to A to B f of A plus B minus x dx. How to prove this? How to say that this is right? I see this is A to B fx dx, and I see it is another function. It means that it has been substituted somewhere. Okay. X has been substituted by A plus B minus x. Both are linear functions, both are continuous, so we can do the substitution. Both are bijective as well, right? So I'm going to say that I'm going to work on this, and I'm going to say x is nothing but a plus b minus t. I'm going to work on the left hand side. Okay. So I'm substituting x as a plus b minus t, which means my dx becomes minus dt. Okay. When x is equal to b, t will be equal to a plus b minus b, that is a. And when my x is equal to a, my t will be a plus b minus a minus b. Just a second, next one. So it will be b. So we have seen the changes here. So we are going to change it. So I'm going to go this way. A, B, F, A plus B minus T minus dt, and this is A and this is B. And I know how to take care of this minus sign. Just I'll replace the limits. So it will be A, B, F, and then I can replace T by X. Okay, clear? So you see the path? But in examination, you just go from this path to this path. Okay, you should remember this. Clear? You see the logic? Now the next is just replacing A by 0. You'll get the same thing. It's the same result. Okay, you don't need extra a different proof for it. So the sixth property becomes 0 to A fx dx is equal to 0 to A f of 0 plus A minus x dx. And what is 0 plus A? A minus x. So the sixth property is also clear, right? All the 6 properties done? Making sense to you? Okay, next. Now see the fourth question, do the both part without integration. Use the concept, use the properties which we have dealt. I see my first part. It is 0 to pi by 2 sine square x dx, right? So I is equal to 0 to pi by 2 sine square x. Then I'm going to use property, which property? I know sine square x. I know if I get cos square x, the things will become a constant thing, and it's very easy to integrate. So pi by 2 minus x, the limit is also helping me, right? So I is 0 to pi by 2 sine square x dx, which is also equal to 0 to pi by 2 cos square x dx, which means I plus I is equal to 0 to pi by 2, 1 into dx. That is 2I is equal to pi by 2. So I is equal to pi by 4. See B part. तो C part मैं बोर्ड पे फर्स्ट पार्ट कर देता हूँ for the online viewers. Zero, right? So I becomes pi by 4. Now if you see the second question, the B part, you see 0 to pi cos cube x dx is equal to I Applying the same property, property number 5, I see 0 to pi cos cube x cos pi minus x, that is minus cos x. So this becomes is equal to I, right? So I see I is equal to minus I. So 2I is equal to 0. So I is equal to, clear? Now see the fifth part. We are going to talk about the geometry. What does it mean when I say a function is even? When I say even function, by definition we mean that f of minus x is equal to fx. And when I say odd function, it means f of minus x. Example, right? And I can say y is equal to x cube, y is equal to sine x. Polynomials with odd powers plus 0 constant, no constant, okay? So we can say these are, but what is geometrically? When I say even function, it is symmetrical about which line? When I say even function, it is symmetrical about the y axis. So I know it will be something like this, right? Whatever on the right, that same thing on the left. And when I say odd function geometrically, what does it mean? Symmetric about, if I turn my graph 180 degree, it will go on to it, right? It means if I fold it, it will be covering it. And if I turn 180 degree this graph and then paste it, it will be pasted up just above it, right? If I shift it 180 degree, it will be the same thing, right? So that means it is symmetric about x plus y is equal to 0 line, right? Now I know, let's say I have to calculate integration of this function from minus a to a. So I have to basically calculate this area and this area. So it will be twice of this area. So I can say minus a to a fx dx is equal to twice of 0a fx dx, right? This for even function. And when I say odd function, let's say minus a, say a, this is and this is magnitude same, but sign opposite. So they will add up to 0. So I'm going to say minus a to a fx dx is equal to 0. Clear? Now you know how, whenever you see odd function or even function, you know how to handle it, right? Should I rub this? The next property is very important property. So the even and odd property is also clear. When fx is even, when fx is odd. Now see the next property. F of 2a minus x is equal to minus fx. So basically it is talking about, I have to calculate something 0 to 2a fx dx. I have to calculate something from 0 to 2a fx dx. It is talking what about it is symmetric about x is equal to a line. It means we have shifted the origin from 0 to a, and what if it is making a even function? And what if we shift the origin from 0 to a? What if this function becomes an odd function? When I see, let's say I have a function. This is my x is equal to a line. It's symmetric. It means, let's say this is your y-axis, this is your origin, right? So I say, and let's say this is your x is equal to 2a. Clear? And you see that fx is equal to f of 2a minus x. That is, you are going this side, you're going this side, xx. So this is 2a minus x. This. So you see this is symmetric about this line. What will be the integration? Double. It's an even function. It will be double. So I can say if fx is equal to f of 2a minus x. What does geometrically it means? It means it is symmetrical about x is equal to a line. It is symmetrical about x is equal to a line. It means 0 to a and a to 2a will have same area. So I can say 0 to 2a fx dx will be equal to twice of clear? We can prove this by substitution as well. How to prove by substitution? Geometrically, you understood? It is creating a meaning out of it, right? Now see, I'm going to do it using the properties. I can make this as 0 to a fx dx plus a to 2a fx dx. I'm going to substitute x by 2a minus x, 2a minus t. So this will become 0 to a fx dx plus, limit will take care afterward, 2a minus t. So this will become minus dt. Dx will be minus dt. Okay. X is equal to 2a minus t. This is my substitution. So t is nothing but 2a minus x. So if my x is a, t becomes a, and this becomes, okay, it is making sense now. So this will turn out to be 0 to a fx dx plus 0 to a f of 2a minus x dx. And it has already given that fx is equal to f2a minus x, so we can say yes. But this is how we were proving it algebraically. But when we see integration, we see definite integration as a signed area. So we should be clear about the geometry. So what does it mean when I say fx is equal to f2a minus x? I'm simply saying that it is symmetrical about x is equal to a line. Clear? And if I say, let's say, what does it mean? It means if we shift my origin from x is equal to 0 to x is equal to a, this function will turn out to be an odd function. Odd function. And somehow if you draw the diagram, this is your x is equal to a line, it will turn out to be something like this, right? It will be 180 degree shifted, it will be superimposed on it, right? So when I say fx is equal to minus f2a minus x, it means I'm simply saying that by x is equal to a line, it is symmetric about origin, or x is equal to, or symmetric about a comma 0. We would rather say it is symmetric about a comma 0. Clear? When I say anything is symmetric about a comma 0, it means यहाँ से मैं आऊँगा t unit away, यहाँ से मैं आऊँगा t unit away, they will be negative. Clear? Algebraically, we can prove. Simple way, the same pattern algebraically, 0 to a fx dx plus a to 2a fx dx. Now x to be replaced by 2a minus t minus dt. This will turn out to be a, this will turn out to be 0. So finally it will turn out to be 0 to a, and which means fx is both are equal. So both are minus of each other, so they will add up to 0. And if it is neither symmetric about x is equal to a and it is neither symmetric about a comma 0, it means you have to calculate simply the way you were calculating it, right? Can we come to question number 8? So question number 8, we can see 8 part 8. You see it is a mod x. What is it? Even function, where the limit is going from -1 to 1. So I can say 2 to 2 into 0 to 1 x dx. So it will finally be 2, 0, 1 x dx. You can handle this. So 8th a part, you can handle this. Clear? The second, you see it is a greatest integer function. What is the property of greatest continuity of greatest integer function? It breaks at every integral points, it breaks, right? So you're just going to graph it up, or you can simply break into either way. Either you want to graph it up, or you can say 0 to 1 x dx plus 1 to 2 x dx plus 2 to 3 x dx. What will be x here? 0. Two. So final answer will be 0 plus 1 plus 2 into 1. That is 3. Clear? Now C part, I see minus 2 pi to 2 pi. Again, it is going from minus 2 pi to 2 pi, and the function is sine cube x. It is an odd function to the power odd number. So odd function to the power odd number will keep it as a odd. So answer would be 0. So C part is 0. No need to solve it, right? Okay, the fractional part, you're going to do the diagram way. So this is 1, this is 2, this is 3. We have to go from 0 to 3, right? But this is a periodic function. We'll talk about periodic function later on, what is the property to say. But you can see the diagram, you have already coined it up. Thrice of 0 to 1. Clear? So C will be 0. Now, D part. Now D is a good question. You see minus pi to 3 pi, and the function is log sec theta minus tan theta. Is it an even function or odd function, or neither even nor odd? Just check it out. D part. I can say f theta as log of sec theta minus tan theta, and f of minus theta is log of sec minus theta is sec theta, and I know these are reciprocal of each other, so I can say the final it will be minus log. Clear? So is it odd function or even function? Odd function. So I can see from minus pi to 3 pi, I can break from minus pi to pi f theta d theta plus pi to 3 pi log sec theta minus tan theta. So this will turn out to be 0. So it's gone now. We're more interested here. Okay, now see pi to 3 pi. So how to go for it? Can I apply a plus b minus x? So if I say I is equal to pi to 3 pi log sec theta minus tan theta, right? And then I say I is equal to pi, say 3 pi log a plus b. What is sec 4 pi minus theta? Sec theta. And what is tan 4 pi minus theta? Minus tan theta. So it will be. So finally it will be. So I see I is equal to minus I. So final answer would be 0. So you see, you saw two concepts. Clear? Now part E. You see part E, I have root sin x upon root sin x plus root cos x dx. Right? If limit wouldn't have been there, it would have been a little messy question, right? So how to handle it? But the limit is very interesting here. Pi is pi plus 3 plus pi by 6 is making 90 degree, pi by 2. So we can easily apply this. So it will turn out to be, we are just going to do a plus b minus x. So it will be pi by 3 plus pi by 6, that is pi by 2 minus x. So what is sine pi by 2 minus x? Cos x. So there won't be any change in the denominator, but the numerator will change to root cos x. So I have I is equal to pi by 6 to pi by 3 root sine x upon root sine x plus root cos x. Applying property 5, that was property 5, right? Applying property 5, I is equal to pi by 6 pi by 3 root cos x upon root cos x plus root sine x, right? Now I plus I is making some sense. 2i is equal to dx, pi by 6, say pi by 3. So 2i is nothing but pi by 3 minus pi by 6, that is nothing but pi by 6. So I becomes, clear? I think it was an IIT question. But if I see minus pi to pi, okay, I see e to the power x plus 1 x sine x. Is it odd, even, or neither odd nor even? What is it? So instead of thinking of odd even, why can't we think of a plus b minus x? So if I say I is nothing but minus pi, say pi, x sine x upon e to the power x plus 1 dx, right? And I is also equal to minus pi to pi minus x into sine minus x, nothing but upon e to the power minus x plus 1, that is minus pi to pi e to the power x sine x upon e to the power x plus 1. Now these two together making some sense. So I can say this I and this I, right? It is making some sense now. So I can say 2i is equal to minus pi to pi x sine x will be the common part, e to the power x plus 1 upon e to the power x plus 1 will be of dx. Now I will see this as even and odd. Odd, 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 even times makes it even. So I can say 2 into 0 to pi x sine x dx. So I say I is nothing but Okay, so I can say I is nothing but I has reduced down to 0 to pi x sin x dx. Can we apply further property or should we calculate it? We can apply further property. So I is equal to 0 to pi minus x into sin x dx. So now things are very simple now. So 2i is equal to 0 to pi. I can say pi minus x plus x is nothing but pi. So I is nothing but pi by 2, 0 se pi sin x dx. No need to calculate. We have already seen in yesterday that it is nothing but 1. It isn't amazing that sin x, the area is becoming 1 unit. Okay, it's a curve thing. It's a curve thing. And the area is exactly 1. So I can say I is clear. Things are easier. If you see from very basics, things are very easy. Now G is similar to E. There's no difference in the question E and G. You see any difference? No, just the root cos x. So no need to discuss that. H part, I see 0 to pi by 2 d theta 1 plus tan theta. How to go for it? Okay, then what is it? Okay, then the same thing. It will break down to the E and G sort of thing, right? So I can solve it simply by making it I is equal to cos theta upon sin theta plus cos theta d theta. Now applying the property a plus b minus x, again I get I is nothing but 0 to pi by 2 sin theta upon sin theta plus cos theta and d theta. So I see I plus I is nothing but 2i d theta. So I is nothing but, clear? Very easy question. Now see I part. I see 0 to pi by 2 sine 2 theta into sine theta d theta. I'll be tempted to do that way, that under root sine 2 theta, break it into the square part and all. But no need to do that. We can simply apply the property and see what it happens to it. I see I part. I is nothing but equal to 0 to pi by 2 root do it. What will it turn out to be? I will turn out to be, there won't be change in under root part. 2 into pi by 2 minus theta is nothing but pi minus 2 theta. And pi minus 2 theta is, this will become, now how to go for it? Is it going to help us anyway? If I add this two up, what will it be? It's now easy now. I can say 2i is equal to 0 to pi by 2 root sine 2 theta into sine theta plus cos theta d theta. It has given us a way for substitution. What should be the substitution? My u should be equal to sine theta plus cos theta or sine theta minus cos theta, because sine theta plus cos theta will be turned out to be a dt part, right? So I can say my, because sine 2 theta I can write either way with the help of sine theta plus cos theta or sine theta minus cos theta. Okay, 1 minus sine 2 theta is equal to sine theta minus cos theta ka square. So I can say 1 minus sine theta minus cos theta ka square will be equal to root sine 2 theta. Clear? So I can do the substitution. My u is equal to sine theta minus cos theta. My sine 2 theta will be equal to 1 minus and root sine 2 theta will be equal to, so it will be equal to, so I see my 2i is equal to 0 to pi by 2, or let's say I half 0 to pi by 2 root 1 minus u square du. Now I can solve it, the proper integration wala. So you have to find the antiderivative. You know how to find the antiderivative? Okay, so you can solve the question. What substitution, or further you can do the substitution, or just find the antiderivative. Antiderivative, you know how to solve, you know the formula. You can derive the formula in 15-20 seconds, right? So see, the question looks like easier, but it's going to take hell lot of time. Examination mein times tickles like a time bomb. J part. If you see J part, it's a very easy question. See, what will be the answer? Tell me. Same pattern, a plus b minus x. That will turn out to be dx. That will be pi by 2, and 2i is equal to pi by 2. So I will be equal to pi by 4. Clear? The k part. How? We're just going to draw the graph. What is the graph of y is equal to sine inverse sine x? But it's the limit is 0 to 2 pi. It is also symmetric about pi comma 0. It is symmetric about pi comma 0. That is f of, you can either use fx of f2 a minus x, or simply draw the graph. What is the graph of f sine inverse sine x? This is the graph of sine inverse sine x. So what is the limit? 0 to, so it will turn out to be 0. It is also symmetric about pi comma 0. Clear? Good. Now when you see the L part, you will be tempted to do the substitution. What is the substitution should be? Okay, cos square x becomes sec square x dx, and I 2 plus tan square x. So we will be tempted for the substitution, but the moment we see the limits, we'll stay back. Wait, I see 0 to 4 pi. Tell me, what is the period of cos x? What is the period of cos x? 2 pi. What is the period of tan x? Pi. Pi. What is the period of cos square x? Pi. And what is the period of tan square x? Pi by 2. So what will the LCM of the time, the whole function? What will be the time period of this function? Pi. So I know 0 to pi, pi to 2 pi, 2 pi to 3 pi, 3 pi to 4 pi. So I see that if f of x plus t is equal to fx, it means it has a time period of t. Right? The period is t. So it is repeating after every t. Let's say I have to find 0 to nt of fx dx. So can I say this is nothing but n into 0 to t fx? I can say it. Clear or not clear? Not clear? Clear? So 0 to nt fx dx, it will be n into 0 to t fx dx. Clear? Now, this question I see the time period, the period of the function is cos square x into 2 plus tan square x. The period becomes pi. So I can say 0 to pi dx upon now what to do? How to go further? Can I do substitution? 0 to pi? No, I cannot do the substitution. Pi minus x, is it making any sense? If this is, things will get little, we'll break it, we'll break the function. We'll break the function 0 to pi by 2 dx upon cos square x into 2 plus tan square x plus 4 into pi by 2 to pi dx upon cos square x into 2 plus tan square x. Now 0 to pi by 2, my tan x is continuous and bijective. So I can do the substitution. I can do the substitution. So my final answer would be 4 into 0 to pi by 2, where x is changing from 0 to pi by 2. We'll take care of the limit later on. Cos square x will go up. That will become sec square x. That will become dt upon 2 plus t square plus 4 into pi by 2 to pi dt upon 4 plus t square. This is nothing but tan inverse. वो वाला जो था x square plus a square वाला. We can handle this. We can handle this. Okay. Okay, we can handle this. So now, how to go for it? Solve it, and then again replace it to by x and apply the limit. You can get the area. You can get the area, and then things will be fine. Okay, clear? So first, we use the concept of periodic function. Then we use the concept of the interval breaking, because I have to do the substitution finally, because the moment I saw cos square x, I was tempted to make it sec square x because things are making easier for me. But we have to maintain the interval. Okay, can we go to the next page? L part. We were explaining it. Okay. What was it? Just the question is repeat the L part. Okay. Okay. See, the function is 1 by, basically the function becomes sec square x into 2 plus tan square x. We see basically it is a product of two functions, and the period of tan square x is pi by 2, and the period of sec square x is pi. So the time period, the total time period of the function turns out to be pi. The period of this function is pi. So I can say that, okay, 0 to 4 pi fx dx is equal to 4 into 0 to pi fx dx. Right? The period of the function is pi. So we can say, okay, whatever the area will be between 0 to pi, it will be same as pi to 2 pi, 2 pi to 3 pi, and 3 pi to 4 pi. So it means we are getting the same area adding up 4 times. So 4 can be taken out, and we can break the function into 4 into 0 to pi fx dx. Now, since the function is 4 into 0 to pi upon 2 plus tan square x, we see this function is easily substituted by tan x as t. But last time we learned that during the substitution in definite integration, we have to be very careful about the continuity and the bijectivity of the function. As we see, we are substituting tan x as t. So tan x is not bijective in 0 to pi, neither it is not continuous. So we have to make this thing as a continuous thing. So we are going to break the function into 4 into 0 to pi by 2 upon 2 plus plus 4 into pi by 2 to pi now it is very safe to do the substitution. We can take the substitution u as tan x and we can create the value out of it, right? Clear? Okay, next page, sir. So the first part we have already dealt, that if a function is a periodic function, it means fx is equal to f of x plus t, right? Or x plus integral multiples of t. They are equal. It means it is a periodic function with time, with period is t. Now if I say 0 to nt fx dx, it is nothing but we are finding the n folds of the same area. And if I can find the area of one fold, I am just going to multiply with n folds. So this will become. Now let's say the second property is saying that let's say if you are not starting from 0, we are starting from a and going to a plus nt fx dx. Will will have any effect on the answer? No, a won't have any effect. The answer will remain same. How? Why? Why a won't have any effect? First we are going to see geometrically and then we are going to see algebraically. If you see, let's say I am taking an example of sine function, right? I have started from, let's say, pi by 3 and I'm going till pi by 3 plus 4 pi. Okay, pi by 3 plus 4 pi. So this is my 2 pi, this is my 4 pi, so I'm somewhere here, right? So I see the area will be this, 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 and this. Whatever portion is left here, you have taken care of, right? So basically, we are just a has having no effect on the a. Now, how to do the algebraically? Let's see how to do algebraically. We are going to break this as 0 to a plus nt fx dx minus we can say this. The meaning is same, right? Now this part I can write that as nothing but 0 to a fx dx plus a into a plus nt. Just a sec. So fx dx 0 to a. I can write 0 to a. 0 to a is a plus nt. Now it's easier now, right? Now we can make the sense out of it. That okay. It means that 0 to a we are going fx dx. We have just added it up and then we got it. So we must subtract this part. So basically we are coming down to the geometry part only, that this part has been taken out from here. Okay. So this is clear that whenever we see a to a plus nt, things will, or we can do the substitution as well. We can prove this by substitution as well. We just have to x as nothing but t minus a. Okay, so this will be replaced by 0 and this will be replaced by nx and things will be fine, right? Okay. Can I do this? Okay. So in time period, in the periodic function, two properties very important. When I say 0 to nt, it means we are taking the area of n folds, right? When I say a to a plus nt, a doesn't matter because we are starting from some and ending after the same fold. So the area will remain the same. So we are going to multiply, we are going to find the area of one fold and then multiply to n folds, right? Let's say I have something called, in the same question, let's say I have a periodic function with time period t fx dx. The limits is going from mt to nt. So I can say this is nothing but n minus m into 0 to t ft dt fx dx. How? Very easy to prove. I'm going to simply say that okay, it is 0 to nt fx dx minus 0 to mt fx dx. So this is nothing but n into 0 to t fx dx minus m into 0 to t fx dx. So finally it will be. So these are the properties which you won't have to prove every time. This is very basically very natural to you. Now you know how to prove it, and then you can easily apply it, and it won't be difficult to keep in mind. Okay. And we go to the next slide. Yeah, we'll be proving. Okay. Now, see the nth question. The nth question is talking about 0 to 2 pi sine to the power 100x into cos to the power 99x dx. Right? This is my function. Now, if you see, this is nothing but my I. Clear? Now, is it symmetrical? Is it fx is equal to f of 2 pi minus x? Is it true? See, is it true? So what does it mean? It is symmetrical about x is equal to pi. When I say my function is symmetrical about x is equal to pi, it means 0 to pi and pi to 2 pi will have the same area. So I can say twice of 0 to pi sine to the power 100x into cos to the power 99x dx. Right? So my I is nothing but my new, this is now the thing we have to calculate. Now if I say 0 to pi, now see here, if I say fx is equal to f pi minus x, are they equal or minus? See, if I put pi minus x, no change. This will be negative, odd power, so it will be negative. So it is symmetric about, it is symmetric about pi by 2 comma 0. So I can say, clear or not clear? So the final answer would be 0. Understood? First we applied simple, we have applied 2a minus x property twice. The first way we saw that okay, it is symmetric about x is equal to pi line. Fine. Then later on we realize that it is the rest part is symmetrical about pi by 2 comma 0. So the function was somewhere like this. If I say this is my x is equal to pi line, This is pi by 2. It was something like this. It was something like this. This was adding up to 0 and there were mirror image. A rough, I am not saying this, but what is happening in the property wise. Okay, the function has something like that. Now it's a very standard problem of definite integration, which the O part is. It's a very standard example. I'm sure you must have seen it or you must have done it. Okay, so if you see I is nothing but, so first equality is very easy to prove, simple, right? So 0 to pi by 2 log sine x is equal to 0 to pi by 2. I don't have to prove the first part. I have to. Simple. A plus b minus x, that is pi by 2 minus x. So sine pi by 2 minus x is cos x. So I have got this. Clear? Now I am going to add it up. So my 2i becomes 0 to pi by 2 log of sine x cos x. Because log a plus log b is nothing but log ab. Right? So I can say log sine, and we can do multiply and divide, little manipulation. So I can say 0 to pi by 2 log sine 2x minus 0 to pi by 2 log 2 dx. Clear? Now things are here different. This is my 2x. This is my 2x. So I can make it t. So 2i is equal to 0. I'm not going to take the limit, बाद में करेंगे. So log sine t and 2x is t. So dt is equal to 2 dx. So dx is nothing but dt by 2. Clear? Now my x is 0, so t becomes 0, and when my x is pi by 2, pi minus 0 to pi by 2, this becomes log 2 into pi by 2. Clear? Now here is the thing. Is it symmetric about x is equal to pi by 2? This is symmetrical. So I can say this is twice of 0 to pi by 2. So I can say 2i is nothing but 0 to pi by 2 log sine x dx minus pi by 2 log 2. And what is this? I. So my I becomes clear. So this is a very standard example, very standard problem, and a good question. Okay. So till here, O part, no issue. Everything is fine. Okay. Now we are going to talk about again the accumulation function thing, and using that accumulation function, we are going to prove the further properties. We are going to see how things are happening. Okay. Above till P, yeah, it's fine. That was O now. Okay, now see, the first part is nothing but a differentiation of an accumulation function. And from the very beginning in the class, I proved it that, okay, if my fx is a to x ft dt, right? So I had to find what it will be. Okay, so we saw that f prime x by first principle, that a into x plus h ft dt minus a into x ft dt upon h, right? This was the story. And then the above thing turned out to be x into x to x plus h ft dt upon h. eh? And we know that fx where m is the smallest value of fx and m is the largest value of fx. So we know this inequation, right? And when b minus a is replaced by mh, it means we are shifting from x to x plus h, x to x plus h, a very small value, which means my least value and largest value both will be equal. So I can say m is equal to fx by h, limit h approaching 0, is equal to capital M. So here we can say my f prime x will be equal to fx. Clear? So differentiation of an accumulation function is fx. Clear? Or any problem? Easy to understand? Okay. Now the next property we are going to prove in the similar fashion. Here it is not simple xa, it is ux vx. It's just limits are written as a function of x, not simply x, not simple constant, but as a function of x. So we have already discussed last time also. Let's say if my fx is a into x ft dt. So if I say f of vx as my new function gx, so it will turn out to be a into vx ft dt. And if I have to differentiate this part, means d by dx of a vx ft dt, this will be equal to g prime x, which will be equal to f prime vx into v prime x. We see fx is this, so what is f prime x? Fx. So what will be f? Making sense now? Okay, so if you see fx a as a function of vx, you're going to think of a composite function, differentiate the composite function. While differentiating the composite function, we have to use the chain rule. That is why v prime x is coming out. Clear? I took a simple case here. Now the question is, in the below also we have the same story, right? So we are just going to break it. That ux vx ft dt, which I can easily write as 0 to vx ft dt minus 0 to ux ft dt. Right? I can write my that thing in this way. Now I have to differentiate it. Derivative of our difference is difference of the derivatives. So I can say d by dx of ux vx ft dt is nothing but f of vx v prime x minus f of ux u prime x. Clear? Easy to handle, easy to prove, but you should remember it. Okay, normally what happens, you do fvx, you do fux, you forget about v prime x, you forget about u prime x. The reason you forget that you actually miss the basics, you miss the basic that okay, we are not differentiating a function, but we are differentiating a composite function. Okay. Now if you see q part, you have to find the slope. Slope is nothing but dy by dx, the rate. Okay. Now the function is y is equal to the limits are varying from sine x square to x cube, and the function is sine theta d theta. The integrand is sine theta. So we have to find, first we have to find the general expression of dy by dx, and then we are going to find the slope at x is equal to 0. So we are just going to put the value of x as 0 there. Whatever the value we get, that will become the slope. We have to find the slope or equation of line, just the slope. Okay. So how to go for it? So y is nothing but x square x cube sine theta d theta. So dy by dx is going to be sine x cube, not x, sine x cube into 3x square minus sine x square into 2x. Now we had to find dy by dx at x is equal to 0, है ना? So it means 0 minus 0. Clear? So the slope is 0. When I say the slope is 0, it is basically a horizontal line parallel to x-axis. R is little c, then R part, how to do it? Think about it, R. I give you 2 minutes to solve question number R. How to go for it? I see t square ft dt is equal to 1 minus sine x. So how? Any clue? No clue? Did you get any answer from online? No answer? Okay. So here I'm going to say that sine x 1 t square ft dt is equal to 1 minus sine x. This is a story. I'm going to call this as gx. Okay. So I'm going to find g prime x. So first I'm going to differentiate left hand side. Second I'm going to differentiate left hand side. So I see a constant up, so it will be 0 minus, this is nothing but a function. So I'm going to say sine square x f sine x. What will be the chain rule? Cos x. And what will be the right hand side? Minus cos x. Okay. Now, this thing, cos x and cos x is true for any real number. So x and x will go off. So it will turn out to be sine square x f sine x. So my f sine x becomes, you don't have to say cosec square x because we don't have to find f of sine x. You have to observe that f of sine x is 1 upon sine square x. So what does it mean? It means fx is excellent We have to find f prime. So further we have to differentiate. So what will be f prime x? X cube. Okay. And just a sec, x to the power minus 2. So this will be minus 2. Okay, minus 2 by x cube. Now we have to find f prime of 1 by root 3. So it will be minus 2, 3 root 3. That is good. It was just using the concept that you know how to differentiate this part. Okay, you must have got little panic by seeing t square out of ft. Think of gt. If this is making any trouble to you, make it gt. So it will be g sine x. Getting the idea? G sine x. And what is gt? T square ft. Put it. You will get the answer. So whatever you see inside, don't worry about it. It is nothing, but it is depending on it. It's a different variable story. You don't have to worry when you are differentiating with respect to x. The other, when you are differentiating something with x, the other thing which is not dependent on x becomes a constant. Now, the s part, I have to find that it's a limit question, right? I see. Okay, we remember when we were studying indefinite integration, the example which we took when we were not that we developed a theory that okay, some of the functions are not hard but impossible to write with the functions we have in hand, and we took the example of e to the power x square, and that is a very statistically important function that makes a bell shape, and we tried to find okay, what will be the shape of the graph. It turned out to be something like this, and it turned out to be something like this. So tell me, I see 0 to x ex square dx chi square upon 0 to x e to the power 2x square dx. So it is going from 0 to x, an infinite area, and we are squaring that up upon again infinity. So it is of the form infinity by, this is the indeterminate form, infinity by infinity. Which rule should we use? L'Hopital. L'Hopital, what did L'Hopital say? If you see 0 by 0 form or infinity by infinity form, you can differentiate it. So I see limit x approaching infinity 0 to x et square dt. Okay, x square is there. Ex square dx square upon 0 to x e 2x square dx. Right. I'm going to differentiate numerator and denominator both. So first, limit x approaching infinity. This is some function to the power 2, so I'm going to write 2 into this function. Right. And this part, I know how to differentiate it. Clear? Upon, I know how to differentiate this. Clear? Okay. Now still we have infinity by infinity form. Right? We can further. First we can do some. 2 will be gone. This will be gone. This will be gone. But still we have infinity by infinity form. So we can go further. L'Hopital we can apply. So the above thing will turn out to be into 2x, and this will turn out to be x square into 2x. Didn't we do any mistake now? Let's see. 0 to x e to the power x square dx square upon 0 to x e to the power 2x square dx. So this was the question. Yes, this was the question. So we did twice of 0, twice of this, differentiating ex square dx, right? Okay, twice of this and differentiating this ex square. Then further we have to differentiate it, huh? We are going to differentiate this e to the power x square. Okay, this, and then the differentiation is this e to the power x square, and then further. Okay. Twice of 0 to x e to the power x square dx. Now I'm going to differentiate this thing, so it will be e to the power x square. E to x. So it's fine. It's fine. E to the power x square. Okay, fine. Because we are not inside. It can be anything. It can be t also, right? So it's okay. Clear? Understood? You have to do the simple. You have to do the differentiation. You have to understand the L'Hopital. You have to see. Okay, whenever we have to use L'Hopital, when we see 0 by 0 or infinity by infinity. But when you were studying differential calculus, they must have warned you that you don't have to use L'Hopital every time. You have to be very careful while using L'Hopital. Now let's say the t part. This is a different story. See, the limits are going from a to b. You have inside a function which is dependent on x and t as well, but we are not integrating with x, we are integrating with t. So x will be treated as a constant only for that. For this integration, x will be treated as a constant only. And then y is this. Okay, now we have to prove that this dy by dx will be equal to a to b d by dx of this function. How to prove it? Whenever we have to differentiate something, what we have to do? We have to always think of first principle. So we are going to think of first principle only. So I see that y is nothing but a to b f x t dt. Right? dy by dx is nothing but a to b fx plus h comma t dt minus a to b fx t dt upon h. Any issue? No problem. We haven't played anything with we just use the basic definition, right? Now we can write this as ab. We can take everything inside fx plus h comma t minus fx comma t upon h dt. You know what is it? When we are going to differentiate by x, this will be the story because t will be treated as a constant. We are not wiggling with t, we are just wiggling x. What is differentiation? How much we wiggle x to find how much my y wiggles. Now, if we wiggle x, how much my y is wiggling. We are just seeing, we are just wiggling x. We are not playing with t, same t. We are just wiggling x to check how my y is changing. It means I am just doing d by dx of fxt by first principle. So I can say clear. So whenever you see anything like a to b into some composition function of xt, what final answer if you have to take out, what you have to find out dy by dx, what you have to do, you just have to go inside, differentiate all the x thing, t will be treated as constant, whatever expression come with t, that will be integrated to find the answer. Okay. Now u is a little difficult and little tricky, because why? See the u theorem, we have y is not only depending on the limits, the x thing is not only with limits but also with inside the integrand. Initially we saw first case, okay, we only had this, here we had only t. Then we saw, okay, we had this constant thing, we have this. Now we saw a mixed case, right? And we saw, uh, whenever we say that y is like this, when we have to differentiate, we just have to write f of x, v prime x minus this. Normally you don't have to prove it, but it's important because it's difficult to keep in mind. It's a long thing to keep in mind, right? So you may get confused also. So we must understand how this is coming. Once we see it, it will internalized and we will be able to produce it whenever we want to. Okay. You have y is equal to ux vx fxt dt, which I can write 0 to vx fxt dt minus 0 to ux fxt dt. Clear? dy by dx I can write 0 vx plus h fx plus h t dt minus 0 vx fxt dt. I just wiggled x here, x plus h, right? The same story. Clear? Not clear? Clear? Now, I can further write it as u to vx plus h minus plus minus see this thing, I can write this as and same pattern as that. So we don't have to prove both the way. Just left hand side is proved, right hand side will itself will be proved. So I see I've added these additional term. What is the additional term? I'm just wiggling with the inside x. I'm not playing with the limit. So you see, I see this wiggling, I see this wiggling, right? In this case, I'm just wiggling the limit. I'm not wiggling the inside thing. And here, I'm wiggling the inside thing, but I'm not wiggling the limit. Clear? See the idea. So when I don't wiggle with the inside thing, this thing will remain a constant thing. So the general formula will turn out to be f of x plus h comma v x into v prime x, है ना? क्योंकि x plus h को मैं लिमिट 0 डाल दूंगा, this will turn out to be x. Okay. So this idea is clear that this is nothing but fx comma, because t के बदले vx आएगा into v prime x, and this will be we are wiggling with inside thing. We are wiggling with inside thing. So it will be limit will remain inside, limit will remain outside, it will go inside. D by dx of clear. Same story will turn out to here, that f of x ux into u prime x plus u minus f of x vx plus 0 to, ठीक है? So finally we'll arrive to fx vx minus fx ux, because this will be the minus part and this will be the plus part, because minus minus will turn out to be a plus thing. So it will be ux to vx d by dx fx t dt. Clear? Just simply, should I do it? Let me do it. So I'm just rubbing the first two lines so that I can come up. Okay. So I see fx comma vx into v prime x plus 0 to vx d by dt of fxt dt. Okay, minus fx ux u prime x minus 0 to ux d by dt of fx t dt. Clear? So finally this will turn out to be fx vx v prime x minus fx ux u prime x with a plus sign. Last term is with a plus sign. 0 ux to vx d by dt d by dx of fx t dt. Clear? Making sense now? So whenever you see this, how to remember it? First, I'm going to apply simple t की जगह vx आएगा, because it's in the limits. So t will be replaced by vx, and then the chain rule fx vx v prime x. Similarly, the below part f of x ux u prime x. ठीक है? But since we were wiggling all the three things together, there will be an additional term which we have seen it. So it will turn out to be we have to partially differentiate the inside x thing. If that thing will turn out to be a differentiated form of x and the t, and that will be integrated to give the limit as vx and ux. Clear? Normally in books they ask you to mug this result so that you can apply in the questions, because they don't ask the proof, but you should know, because once or twice you will be proving at your place, that will be totally assimilated, and then during the examination when it will appear, you won't panic and you will be able to regenerate. Next slide. Today's slide, I gave 3 pages. See, when we were using something of sine to the power mx into cos to the power nx dx, right? Whenever we are handling these type of integrations, even in indefinite part, we had this 4 issues. I'm putting m here, n here. Odd, even, odd, even. As long as both were odd, we were having no issue. When one of them were odd, also it was no issue. No issue. Here, it turned out to be a little messy thing, right? So these are the basic normal concepts we use it. This is solved by reduction formula. We have already been exposed little to reduction formula. We'll see how. You see the idea? If you see both the powers as even, you're going to see this, right? So let's say I have to say that 0 to pi by 2 cos to the power nx dx. This is nothing but in. I'm going to say this is nothing but in. Okay. I'm going to take by parts. By parts, I'll take cos to the power n minus 1 as 1 and cos x as other. So cos x dx will be my function which can be easily integrated. So I'm going to write this as cos to the power n minus 1 x. Cos x dx का integration is sin x minus then you have what is the derivative of cos to the power n minus 1 cos x? Into minus sin x to sin square x dx. No issue till here? So I can see that in is equal to sin x into cos to the power n minus 1 x plus n minus 1 into cos to the power minus 2 x dx minus n minus 1 into cos to the power nx dx. I just replaced sin square x as 1 minus. So it will turn out to be something like this. Clear? This is nothing but in and this is nothing but in minus 2. So I can say that n into in, I'll shift my n minus 1 to the left. So n minus 1 plus 1 is n. In is equal to sin x cos x plus n minus 1 into I to the power, and I can say 1 by n. I can say this. Now this is nothing but a recursive thing. Now in is going from 0 to pi by 2. So I also say 0 to pi by 2. This will vanish. This thing will vanish. So finally I will be left with this. So I got something like in is equal to n minus 1 by n in minus 2. Clear? Limits, we are taking care of limits, 0 to pi by 2. That is why this goes off. We are left with this recursive thing, okay? It means I2 is nothing but 2 minus 1 upon 2 into I0. I4 is nothing but 3 by 4 into. So you see the recursive thing? Okay, good. So please note this thing. We'll go further. So I got In is equal to n minus 1 by n In minus 2. Now I'm going to find various values. I'm going to see a pattern कि जब 0 है तो क्या होगा, 1 है तो क्या होगा, 2 है तो क्या होगा, 3 है तो क्या होगा, 4 है तो क्या होगा. We'll go till 5, 6 till we are able to get our pattern. Okay. Now, when and what is In? Cos to the power nx dx 0 to pi by 2. Clear? When I put 0, this becomes constant function. The value is. And when I say cos x dx when n is 1. When I say cos square x dx, when I say cos square x dx, it means this is equal to n minus 1 by n. N is what? 2 minus 1 is 1 by 2. And what is I0? 5. So I got something like 1 by, don't multiply it. We are going to generate a pattern out of it. Okay. We are not going to simplify it. 1 by 2 into pi by 2. Clear? Now see, third. So I see I3 will be equal to 3 minus 1 by 3 I1. That is 2 by 3 into 1. Clear? For 4, I4, 3 by 4 I2, that is half into pi by 2. है ना? So I say 3 into 1, 4 into 2, pi by 2. Clear? You're getting the pattern now? Till 6, we'll be having our pattern. I5, values तो अभी पता चल गया, pattern तो अभी पता चल गया, just a hunch. एक बार reconfirmation. I5 is nothing but 4 by 5 into I3, है ना? And I3 is 2 by 3. So you are getting the pattern now. 4 into 2 and 5 into 3 into I5 was 1. Clear? So 6 करने की जरूरत नहीं है. It will be 5, 3, 1, 6, 4, 2, pi by 2. Okay, so here we got something like if 0 to pi by 2 cos to the power nx dx will be equal to, I see, when I see even, मैं 0 पहले evens को देख रहा हूँ, ठीक है? So I see pi by 2 everywhere. Pi by 2 into something. In numerator, I see a series of odd numbers beginning from 1 and ending at n minus 1. Upon, in down, I see series of even numbers beginning from 2 ending at n. This is the story of n even. Clear? And when n is odd, I see a different story. I see here 1, 1, 1, 1. Now in numerator, I see In numerator, I see even numbers and ending at n minus 1. Enough? See, 3 minus 1, 5 minus 1. So 2, 4, n minus 1. And in the denominator, what we are seeing? 3, 5, 7. So 1, 3, 5, 7 till start with 3 only. 3, 5, 7 till we ending at n. Done? And this is also equal to 0 to pi by 2 sine to the power nx. Clear? Why they are equal? Pi by 2 minus x, or even graphically you see this is your sine function, right? And this is your cos function. This is the story of sine x and cos x. They are both symmetrical. So whatever the area is here, the same area will have. And when you multiply any, when you were doing calculus, sketching the graph, what did you do all the things like when you have y, when you know the graph of y is equal to x, how to handle fx to the power 2, 4, 6? You know how to deal with it? When you know how the graph is y is equal to fx, you have to do fx to the power 1, 3, 5 even. You didn't do that? Okay, when we'll be dealing area chapter, we'll first concentrate first half an hour totally in the sketching of graph, because that is more important. If we are able to sketch the graph, application of integration, 90% of the thing has been finished. At the moment you have a command on graph, and the rest 10% you have already done in definite integration. So in application of integration, there will be hardly anything new to learn. Okay, but when we'll be finding the area, we are not going to find the signed area. We are going to find the area. When we have to find the area, we have to find the area. We are not going to say that sine x dx 0 to 2 pi is 0. We are going to say that is 2. It means we have to take everything in mod. We have whatever negative portion we have to switch it to positive. So if you have a command on graph, you have a command on definite integration properties. If you have a command on finding the points of intersections, application of integration has nothing new to test. Okay. So it should be mugged up. This thing you are not going to derive every time. These things need to be mugged up. Okay. Okay, now see, the moment we see inequations in integration, the first inequation we have already we have introduced you. What was that inequation we talked about? Because integration is nothing but talking about area. When it is talking about area, we have already told you how to find overestimating and how to do estimating. Overestimating and estimating में एक तो छोटा सा difference था. It was just a little difference, right? And we were approaching from left side and right hand side. But let's say I'm going to create. I got certain area. I got certain area. I'm going to create one rectangle. This. I'm going to, let's say this thing is going from this. Okay. This is one area that will be equal to m into b minus a. And let's say this is my minimum point. M into. So that is very sure that the area will lie somewhere between these two. Getting the idea? This inequality is very normal, very common, easy to comprehend. Okay. So whenever you see integration with inequality, always think of this rectangle thing. Because integration, whenever we are going to see definite integration, we are going to see it as an area. As an area, so we are going to see, okay, the largest rectangle I can make out of that area, and the smallest rectangle I can make out of that area. And my area will always lie between the area of the smallest rectangle and the largest rectangle. So the question is, question number 2, just, yeah. I have my function, it is lying from 1 to e, 0 to 1 ex square dx. We have to prove this, right? Basically, we have to integrate the function e to the power x square from 0 to 1. I know certain thing about ex square. I don't know how to sketch the integration of ex square dx, but certainly I know how to sketch e to the power x square. I know how to sketch e to the power x square. It is an even function. When you have an even function, what does it mean? It means that it is symmetric about x-axis. Now, and we know ex square is an exponential function which will be increasing exponentially. At x is equal to 0, it will definitely be 1, and it will further go on. And at 1, at x is equal to 1, it will be 1 comma e. Clear? So this is 0 to 1 mein, this is the minimum point and this is the maximum point. So I can say 0 to 1 ex square dx. What is the minimum value? 1. What is b minus a? What is the maximum value? What is b minus a? Hence, clear? Not clear? Basically, it is talking that, okay, it's just telling that the area under the curve will be greater than this portion and smaller than this rectangle. Easy to say that. Try question number 3. Let's see whether you have been able to grasp this concept or not. You know the graph of 3 plus x cube under root? Can you sketch it? Can you sketch it? Can you sketch it y is equal to x cube? If you can sketch it y is equal to x cube, you can easily sketch it under root 3 plus x cube. Kaise? Okay, first I'm going to draw y is equal to x cube, then x cube plus 3. It means I have to shift my y ऊपर की तरफ. जब मैं 0 पुट करता हूं तो 1 आता था. जब 0 पुट कर रहा था 0 आ रहा था, but now it is coming out to be 3. So it means I have to shift my thing up. So my y is equal to x cube has been shifted up 0, 3 पे. Then I'm taking under root. Under root. I cannot take the under root of negative numbers. So whatever in the left side wipes off. Whatever on the left side of x-axis wipes off. I have to see things from 1 to 3, but first I have to see कि graph कैसा हो रहा है. Now I'm taking a square root. When you see when you have to draw, when you know the function fx, you know how to draw y is equal to fx. Then we have to draw y is equal to fx ka under root. So how to go for it? First of all, the domain. The second thing, you have to see the pivot points. I'm going to show you. I'm going to actually discuss first that part only. How to handle the curves. Let's say this is my function y is equal to fx, and I have to draw y is equal to fx ka square or any even. Right. Now the point here is I know my function. If I square it up, everything will turn out to be positive. So I'm going to make first everything positive. Right? First step, make everything positive because we have powers even. Now, will the zeros change? When I square 0, what I get? 0. So wherever I see 0, I'm going to make it a fixed point. This is fixed. This is not going to change. This is fixed, not going to change. This is fixed, not going to change. What about 1? not going to change. Let's say this is my 1. Let's say this is my 1. Let's say this is my 1. Okay. So these are basically my fixed points. Okay. When any number is greater than 1, its square gets greater or smaller? More greater, ना? Let's say अगर 1 से 2 तुम गए, 2 का स्क्वायर क्या हो गया? 4. Larger. So whatever I see, this is also 1. Whatever I see above 1 will increase more. Means it will be shooting up more. So I'm just going to shoot it up. I'm going to shoot it up. It will have larger, steeper, right? Steepness has been increased because of the even power, because numbers are greater than 1. What happens when the numbers is lying between 0 to 1? It gets decreased. Okay. So I'm going to pull down. This is my this thing. I'm going to pull down here. So this will be something like this. This will be something like this. This will be something like this. Pull down. This will be something like pull down. Clear? Things have been pulled down. Whatever was lying between 0 to 1. So the pivot points were 0 and 1. So between 0 to 1, whatever things were, it was pulled down, and whatever things were above has been increased. Now everything is fine. Now the only issue with the graph is whatever the kink we got while taking the mod. सबसे पहला स्टेप क्या था? मॉड था. तो हमने किंक्स मिले थे, हमें यहाँ पे किंक्स मिले थे, यहाँ पे किंक्स मिले थे, यहाँ पे किंक्स मिले थे. I have to make it smoother so that my function is differentiable at that point. Clear? Now let's say it is 3 or 5 or 7. The power is now odd. So remember, this was my line y is equal to x. My pivot points were 0, 1, minus 1. Whatever is between 0 to 1 will be pulled down, and whatever this is shooted up, pulled down, pulled up, shooted up. So this was my y is equal to x cube. Clear? So what to do when we have to do? We have already created y is equal to fx. We have to spot the pivot points. Now the pivot points are minus 1, 0, 1. These three are my pivot points. Above 1, shoot up. 1 to 2, pull down. 1 to minus 1, 0 to minus 1, pull up, shoot down. Clear? No doubt in this? So you know how to handle fx to the power even, you know how to handle fx to the power odd. When you have to, up now the question is half, 1 by 4, 1 by 6, root. So the story remains the same. I want everything to be positive. I want everything to be, whatever जो negative है वो तो खत्म हो जाएगा. I will wipe it off. I'm not taking the mod. I'm just going to wipe it off. That will not be under my domain. Under root 0 is 0. Under root 1 is 1. अच्छा, 0 से 1 के बीच में let's say half है और 1 by root 2 है. बड़ा कौन होता है? ये बड़ा होता है या बड़ा होता है? तो मतलब रूट लेने पे इंक्रीज होता है ना, एंड देन वहां पे डिक्रीज होता है. दैट इज व्हाई स्क्वायर रूट का फंक्शन ऐसा होता है. y is equal to root x, y is equal to x square, y is equal to root x, and this is y is equal to x line. Remember the relationship, they are invertible functions. Clear? Okay, now coming back, we'll take the fresh look on graphs next class in integration, application of integration class. So don't worry, we'll also handle all the graphs, whatever we did in differential part. We'll do from the sketch, right from 0. Even function, origin, symmetry, everything. Right from 0 we'll do, okay? Now, 3 plus x cube, I can simply make out that it is an increasing function, right? Either through graph, either through dy by dx, whatever. My graph is the easiest way to say. If I know how to draw the graph, I don't have to do dy by dx, d2y by dx to check and all, right? Now I see under root 3 plus x cube as nothing but an increasing function. So obviously the minimum point will lie at 1 and the maximum point will lie at 3. So what will be the minimum point? 2. My fx is under root 3 plus x cube. So what will be m? 2. 3 plus 1. And what will be capital M? Root 30. And what is b minus a? So 2 into 2, 1, 2, 3, 3 plus x cube dx is equal to 2 root 30. Very easy question. If you knew the graph, okay, things were easy, that it is nothing but an increasing function. So at x is equal to 1, we have minimum value, and at x is equal to 3, we have maximum value. See, this thing, the fourth thing is not in the syllabus to prove it, but you just mug it up. Okay, you will note it down. Okay, you will note it this down, that when we have sine to the power m into cos to the power nx dx 0 to pi by 2, when the numbers are small, m and n, you can handle it. Right, when the numbers are pretty big, see the same story, very similar to the last one. When both are even, I got pi by 2, and m plus n starts with down, m plus n minus 2, all the even things down, and individually the first odd things into the second odd things. Okay, and when we have either one of them is odd, no matter if both are even, handle. If one is even, or both are, if one is even, one is odd, or both are odd, we are going to see, okay, that I want in below thing, I don't know whether it will end at 1 or 2, because m plus n can be anything. So m plus n minus 2, m plus n minus 4, and here m minus 1, m minus 3, it can end at 1 or 2, because I don't know whether m is even or m is odd. Okay, this is the story. You should keep it in mind. Number 5, you must mark this thing, right? That sine to the power n, cos to the power n, and then this. Okay. Now see, find the points of local max and local min of a function. Remember differential class? What we used to do when we have to find the local max and local, differentiate and then double differentiate, or rather just see that your f prime x अगर प्लस से माइनस की तरफ आ रहा है, प्लस टू माइनस it is local max, and minus to plus it is local min. This was the story. Now see the function. Y is nothing but 0 to x square t square minus 5t plus 4 upon 2 plus e to the power t dt. You know how to differentiate it? How to differentiate it? I'm just going to think of a composite function. I'll replace x by x square, and then things will be x to the power 4 minus 5x square plus 4 by 2 plus e to the power x square into 2x. I want this thing to be equal to 0. Then only I'll get local, the critical points, not the local max, local mins. When we find f prime x is equal to 0, we find critical points. The critical points can be local max, can be local min, can be point of inflection, or can be a point where definition of function is changing. So critical points, you must understand what's critical points. Okay. So when I say f prime x is equal to 0, it doesn't mean that I'm finding local max, local min. I'm just finding the critical points. Now see this function. I can factorize this further. It will turn out to be x square minus 4 into x square minus 1 into 2x upon 2 plus ex square, right? Right, this is the story. I can further break it down. It will turn out to be x plus 2 into x minus 2 into x plus 1 into x minus 1 into 2x upon 2 plus e to the power x square is equal to 0. This thing will never become 0. It will always be positive. It will always be positive. The critical points I see as, it starts with 2, 1, 0, minus 1, minus 2. These 5 are the critical points. Right. On the extreme right, everything will be positive because x minus 2 will be positive. 2 के इधर सब positive है. right? Here it will be negative because only one term is getting negative. Everything is positive now, right? And then positive, negative, positive, negative. Acha, tell me one thing. I'm just testing you that if I say x plus 1 ka square, then what will be the pattern? At minus 1, sign won't be. It will become an even point. Okay. So you see, I don't have to find double derivative because I have find f prime x. I know how signs is varying. If I go from minus to plus, it is local min. Plus to minus, it is local max. Min, max, min. Clear? Plus to minus, max, minus to plus, min. Clear? Good. Next page. This one. Now let's say another property, which is also very, quite very easy to understand. A to B fx dx will be lesser A to B mod fx dx. Do I have to explain it? This is nothing but area, signed area with a mod sign. And here I'm making all the function as positive. So everything, there is negative components. Here is no negative component, all the positive components. So it will add up to obviously a larger number than this. This inequality is cool. You can handle it. Now the second theorem is property is also very not something which you cannot understand. It's like if fx is greater than gx, then obviously the area will be greater, right? If fx is greater or equal to gx in interval a to b, so obviously the area will also be greater. Clear? And similarly, if fx is positive for x, so our area will also be positive. So no need to talk about it. Sixth question. You see, sixth question, I see pi by 3 to x and then 0 to y. I have to evaluate dy by dx. It means I have to differentiate with respect to x. And I see first part and second part. Differentiate first part separately, I can differentiate second part separately. So first part will be under root 3 minus sine square x. That's it. That's it. Plus, that will be so what is my dy by dx? Simple, this upon this. Clear? Not clear? First term, that's simple. Accumulation function. So I can see that under root 3 minus x square, sine square x, 3 minus sine square x. Okay. Simple accumulation function, the basic definition. So this question was any difficult? It was a simple one-liner question, 5 seconds answer. Seventh. Late. fx is integrable function such that हमें क्या क्या दे रखा है? Integrable function मतलब we can do integration, and we have given one inequality that f of x minus f of y mod is less than equal to x square minus y square, given, right? This is given for xy is the element of a to b. Then prove that. Okay, inequality part I can easily prove now. When I see left part, I can say that okay, a to be fx minus fa upon x plus a dx, the mod will be less than ab mod of fx minus fa upon x plus a dx. I can say this mod of fx minus fa, this part is lesser than this. So I can say this will be less than a to b mod of x square minus a square upon x plus a. I can say this. Now, this will be equal to a to b x minus a dx. Obviously, a is smaller, so it will be positive. So no mod can be removed directly. So it will be x square by 2 minus ax b to a. So I can say that it is nothing but b square by 2 minus ab minus a square by 2 plus a square. A square minus a square by 2 will turn out to be, so I can say a minus b whole square. यही तो था, है ना? Inequality, 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 and then I just calculated it and turned out to be this. Clear? Simple or difficult? This is good. FX, very easy question, but it is not. It is just testing the basic thing, that whether you understand definite integration or not, whether you understand its area concept or not. These are very simple questions. If fx is a continuous function such that fx is positive always between 2 to 10, 2 to 10 interval ke liye, this function is always positive. But I see 4 to 8, this function is integrating to 0. What does it mean? Odd function. I have already said that 2 to 10 it is never getting negative. And at 4 to 8, the area summing up to 0. It means that function is on the x-axis. It means the function is 0 for the entire 4 to 8. 6 lies where? So what will be f6? That is the question. See? When I say fx is positive, it means I am saying my function is totally above x-axis or on the x-axis. So on the x-axis is not ruled out, and the examiner is just checking that whether you are ruling it out or not. Those who will always say that fx greater than 0, greater or positive 0, it means whether he thinks that fx is always positive or he thinks that fx is positive or can be 0, which means it can collide to, it can collide, it be aligned to x-axis, right? That's 0. 8th question, very easy question, just a talking question. Huh? No need to solve it. Everybody understand 8th? Okay. 9th is little tricky. I see x to the power 4 dx upon 1 plus x to the power 6 to the power 2 by 3 dx, integrating from 0 to 1. If I put here, if I remove 1, I get 1. I get here. If I remove 1 constant, I get something here. And if I get x to the power 5 here, I get something there. I'll show you how. X is varying from 0 to 1. So I can any day say that x to the power 6 is greater or equal to x to the power 6. है ना? Clear? It will be greater than x to the power 6. Now, and I can also say that x to the power 6 will be less than x to the power 5. Clear? नहीं समझ में है? X is lying from 0 to 1 ना? So I can come up that, okay, x to the power 4 upon 1 plus x to the power 6, 2 by 3 will be less than or equal to x to the power 4 upon x to the power 6, 2 by 3. Making sense? Right? Clear? This inequality is true. Clear? So what I can say, what is the integration of this? 1. This will remain as it is. What is the substitution needed? पूरे t को ले लो. So t to the power minus 2 by 3 dt, that will be minus 2 by 3 plus 1, that is t to the power 1 by 3 upon 1 by 3. So it will be something. So solve कर लोगे तो यही आ जाएगा. You don't have much time. Solve कर लोगे तो क्या आ जाएगा? 3 by 5 to the power 1 by 3 minus 1. Clear? So the inequality is solved. Clear? Substitute this as t. Things will be fine. It will be very easy now. Now we'll just do 10th. Okay. I have x square and the greatest integer inside, and it's going from 1 to 2. So 2 ka square is 4 and 1 ka square is 1. Between 1 and 4 I see 2 and 3, which means that the square root is lying root 2 or root 3. Matlab I can break my function into 1, root 2, root 2, root 3, 2. dx, dx plus dx. Right? Now 1 to 2, what will be my x? 1 to root 2 क्या होगा मेरा greatest integer? Root 2 to root 3, that is 2 to 3, 2, and 3 to 4, 3. Clear? Now the final answer would be root 2 minus 1 plus 2 into 3 minus root 2 plus 3 into 2 minus root 3. Clear? रूट 2 का स्क्वायर क्या होता है? 2 और रूट 3 का स्क्वायर क्या होता है? 3. So 2 और 3 के बीच में जितने भी नंबर्स होंगे उसका ग्रेटेस्ट इंटीजर क्या होगा? 2. Clear? I have broken. See, the x square part is inside. Okay. Similarly, you can handle mod x square minus x. The critical points are 0 and 1. 0 and 1. So x square minus x means 1, 0. यहाँ positive, यहाँ negative. कहाँ से कहानी शुरू हो रही है? यहाँ positive. कहाँ से कहानी शुरू हो रही है? Minus 2. So minus 2 to 0, it will be x square minus x. ठीक है? Same story, x square minus x dx plus 1 to 3 x square plus minus x dx. Clear? Third question is very good and very good question. You see 0 to x t plus 1 cube dt. It's basically ty plane. It's basically ty plane. And it is making t plus 1. है ना? So I'll say this, and t is varying from 0 to x. T is varying from 0 to x. So I would like to think this way, that my x, and x is just a real number. X is just a real number. It can be integer, it can be non-integer. But I'm sure that n and n plus 1 are integers. So x is somewhere lying between n and n plus 1. So I'm going to break the thing into 0 to 1, 1 cube dx, है ना, 0 to 1 plus 1 to 2, 2 cube dx, 2 to 3, 3 cube dx, and will go on till n minus 1n, n cube dx plus n to x, n to x, basically that will be fractional part. Clear? That will be basically fractional part now, the left part. Clear? Understood or not clear? Understood. So I can see this thing as nothing but 1 cube plus 2 cube till n cube plus n say x, whatever the thing is, one plus t cube, the whole cube. So it is something like n plus 1 ka whole cube into fractional part. Understood? See, the last thing is happening, like I'm going till n tak sab kuch theek hai. N say n x, x is nothing but n plus some fractional part into 1 plus t ka cube dt. So tell me what will be the integer value? N say n plus x, n, and that is n plus 1 ka cube. So it will be 1 plus n ka cube, but it will not be totally to the entire breadth, it will be just to the fractional part. Understood? So it will be, है ना? I know how to sum this thing up. N into n plus 1 by 2 ka whole square, and I know this is nothing but n plus 1 ka cube into fractional part, है ना? Okay, now I'll say mod x, sorry, this greater than function x is nothing but n, so I'm going to replace everything by x. Clear? This will turn out to be a very fine question. Finally, you don't have to leave your answer in n, rather you have to leave your answer in greater than x into greater than x plus 1 by 2 ka plus fractional part into greater than x plus 1 ka cube. Clear? D part you can easily handle. Square root है, 0 to 9 square root है. तो what are the things जहाँ पे change हो रहा है? 0, 1, 4 and 9. So you are going to break everything from 0 to 1, 1 to 4 and 4 to 9. E part is you are just going to draw. This is your 0 to 2 pi. So यहाँ पे सिर्फ 1 होगा, यहाँ पे सिर्फ 1 होगा, rest it will be 0. Negative के लिए क्या हो जाता है? -1 ना? So it will be here. ऐसा होगा. So you know the area is this 0 and this will be minus. So you can find, right? Graphically you can find it. So F part is a very good question. I see minus root 2 to root 2. And I see a polynomial of very high degree, 7 तक जा रहा है. But denominator we see it's a odd even function. So बस ऊपर का जो function है, so I'm going to separate all the even plus constant. So I'm going to separate 3x to the power 6 minus 12x square plus 1 out. Rest will turn out to be a 0 thing. Kyun? Because that is a odd function. So I just have to solve 3x to the power 6 minus 12x square plus 1 upon x square plus 2, which we can handle. Right? This one G, I see x to the power 4 upon 1 minus x to the power 4, and it is going from -1 by root 3 to 1 by root 3.
So I'm not sure what happens, but I see cos inverse 2x upon 1 plus x square. I know sine 2 theta is equal to 2 tan theta upon 1 plus, ये होता है ना, तो sin 2 theta तो मैं दिख गया 2 tan theta upon 1 plus tan square theta. So I can say minus 1 by root 3 into 1 by root 3 x to the power 4 upon 1 minus x to the power 4 pi by 2 minus sine inverse it will be sine 2 theta. So I can write this as nothing but tan inverse x. है ना? So I'm going to separate my thing as pi by 2 minus 1 by root 3 x to the power 4 pi by 2 sorry pi by 2 बाहर निकाल लिया ना, x by 4 upon 1 minus x to the power 4 dx. This is one part minus into 1 by root 3 x to the power 4 upon 1 minus x to the power 4 tan inverse x. This is the even function, but this is tan inverse x is odd function. So this will turn out to be 0. We just have to work it this out. Huh. Okay. So finally it will be 0. No issue. कभी कभी गलती करने से गलत नहीं होते हैं. Okay. We are finished now. Okay, so last sheet, and next class we will discuss the last sheet and then the graphs and then the application. Okay.